For thousands of years, human eyes traced familiar patterns among the stars, mapping constellations that guided travelers, marked the seasons, and inspired myths. Civilizations across the globe, from the Egyptians charting Orion and Sirius to the Chinese cataloging thousands of stars in the Shiji, and the Mayans tracking Venus cycles, developed intricate star maps. The apparent sky was treated as a flat dome, and the faint glow of the Milky Way was described as a featureless band. Observations were limited to stars visible to the naked eye, without knowledge of extragalactic objects or their distances. If you're captivated by the vastness of the cosmos and the wonders hidden among the galaxies, subscribe now. Our journey across the universe's countless stars and worlds begins today. The transformation of this perception began with a single revolutionary tool, the telescope. When Galileo Galilei, in 1609, pointed his handmade refracting telescope toward the Milky Way, he discovered that the soft, luminous band across the night sky was not a homogeneous cloud, but a collection of countless individual stars, densely packed yet discernible. His observation, later published in Sidereus Nuncius, provided evidence that the Milky Way contained numerous individual stars. Galileo's telescope, magnifying objects by roughly 20 times, allowed him to identify Jupiter's moons as discrete bodies orbiting their planet, demonstrating that observational tools could uncover structures and motions invisible to human sight. Over the following centuries, telescopes grew in size and sophistication. William Herschel, building on the work of his sister Caroline Herschel, systematically surveyed the night sky in the late 1700s. Together, they catalogued more than 2,500 nebulae and clusters. Some, they understood, were clouds of gas illuminated by nearby stars, while others displayed spiral or elongated forms. Herschel hypothesized that some of these nebulae might be island universes, an idea so radical that it would take nearly 150 years to confirm. The instruments of the time, though revolutionary, lacked the power to determine distances, and measurements of these objects' separations from Earth were not possible. In 1845, William Parsons, the Earl of Ross, constructed the Leviathan of Parsonstown in Ireland, featuring a colossal 72-inch speculum metal mirror. With this telescope, he was able to observe the Whirlpool Nebula M51 in unprecedented detail. Parsons' sketches revealed its spiral arms, the first visual confirmation of a galaxy-like structure beyond the Milky Way. At the time, astronomers did not have methods to measure the distances of these objects from Earth. The question of the universe's scale culminated in the Great Debate of 1920, held at the Smithsonian Museum of Natural History. Harlow Shapley argued that the Milky Way, estimated to be around 300,000 light-years across at the time, contained all known nebulae, representing the entirety of the cosmos. He based his reasoning on the distribution of globular clusters, which suggested a vast but singular galaxy. Opposing him, Heber Curtis argued that nebulae like Andromeda and the Whirlpool were independent galaxies, each potentially millions of light-years distant. The debate highlighted a fundamental limitation of observational astronomy. Without accurate distance measurements, the nature of these faint, fuzzy objects remained speculative. The breakthrough came with the work of Henrietta Swan Leavitt at Harvard College Observatory. Studying Cepheid variable stars in the Small Magellanic Cloud, she discovered that the period of a Cepheid's brightness variation is directly proportional to its intrinsic luminosity. This relationship, now known as the period luminosity law, provided a powerful tool for measuring cosmic distances. By comparing a Cepheid's intrinsic brightness with its apparent brightness as observed from Earth, astronomers could calculate its distance with unprecedented accuracy. In 1923, Edwin Hubble applied Leavitt's discovery using the 100-inch Hooker telescope at Mount Wilson Observatory in California, the largest telescope in the world at the time. He identified a Cepheid variable in the Andromeda Nebula M31 and calculated a distance of approximately 900,000 light-years a value later revised to around 2.5 million light-years, but still far beyond the Milky Way's estimated 100,000–120,000 light-year diameter. Andromeda was no mere nebula. It was a galaxy, a vast island of stars in its own right. This realization shattered the long-held assumption of a universe confined to the Milky Way. Hubble did not stop there. By measuring the redshift of galaxies, the stretching of their light to longer wavelengths due to cosmic expansion, he discovered that nearly all galaxies are receding from us, with velocity proportional to distance, a relation now called Hubble's law. Galaxies, hundreds of millions of light-years away, move at thousands of kilometers per second. This observation revealed that the universe itself is expanding, laying the foundation for the modern Big Bang model, and confirming that galaxies are dynamic participants in a universe in motion, rather than static, isolated systems. The mid-20th century brought the advent of radio astronomy, opening entirely new windows on galactic behavior. In 1932, Carl Jansky detected radio emissions from the Milky Way, and subsequent surveys identified powerful jets of charged particles from galactic nuclei, some extending tens of thousands of light-years. These discoveries revealed supermassive black holes at the centers of many galaxies, engines of energy that shape their evolution. Observations across the electromagnetic spectrum X-ray, ultraviolet, infrared, and radio demonstrated that galaxies are complex systems of stars, gas, dust, dark matter, and plasma, exhibiting phenomena invisible to optical telescopes. The launch of the Hubble Space Telescope in 1990 revolutionized observational astronomy. Positioned above Earth's turbulent atmosphere, Hubble captured deep-field images of empty regions of sky, revealing thousands of galaxies in a space smaller than a grain of sand held at arm's length. These galaxies ranged from compact, irregular shapes to grand spirals and massive ellipticals, spanning distances from a few million to over 10 billion light-years. If every tiny patch of sky contained thousands of galaxies, the observable universe could easily hold over 2 trillion galaxies, each containing hundreds of billions of stars. Among them, some formed when the universe was less than 1 billion years old, offering a direct glimpse into cosmic infancy. Today, the James Webb Space Telescope extends humanity's reach even further. Observing primarily in infrared, Webb penetrates dense cosmic dust and measures the light from galaxies formed just 200–400 million years after the Big Bang. Its instruments can detect chemical fingerprints in early stars, revealing hydrogen, helium, and traces of carbon, oxygen, and heavier elements forged in the first stellar generations. Webb has identified early proto-galaxies less than 1,000 light-years across, irregular and clumpy, precursors to the spirals and ellipticals that dominate the modern universe. By analyzing thousands of these galaxies, astronomers can track star formation rates, mass assembly, and early black hole growth. Through these advances, a detailed picture of the universe has emerged. Galaxies are not isolated. They cluster, collide, and merge in structures shaped by gravity and dark matter. The cosmic web, a network of filaments, sheets, and voids, extends across billions of light-years, connecting galaxies in patterns that reflect both visible matter and invisible dark matter scaffolding. Clusters like Virgo, Coma, and Fornax contain thousands of galaxies bound together, while immense voids stretch across tens of millions of light-years, regions nearly devoid of matter. Observing these structures informs scientists about the distribution of mass, the influence of dark energy on cosmic expansion, and the intricate evolution of galactic systems over 13.8 billion years. From Galileo's small refractor to the Hooker telescope, Hubble, and Webb, successive generations of astronomers used increasingly advanced instruments to observe galaxies and their structures. Observations revealed details about spiral arms, elliptical galaxies, active galactic nuclei, and the chemical composition of stars. Data collected over time allow astronomers to chart the distances, motions, and interactions of billions of galaxies. The upcoming Nancy Grace Roman Space Telescope, the extremely large telescope in Chile, and the Square Kilometre Array are designed to probe billions of galaxies with high-resolution, mapping cosmic structure, dark matter distributions, and galactic evolution at unprecedented scales. These instruments will enable the detection of faint galaxies, proto-galaxies, and energetic phenomena. The cosmic web, mapping the universe's grand design. When Edwin Hubble revealed that galaxies were independent islands in an ever-expanding cosmos, astronomers faced a new, daunting question. How are these islands arranged across the vast, almost unfathomable scale of the universe? Early on, the assumption was simplicity itself. Galaxies, like the stars in our night sky, were scattered randomly. Yet, as decades of observation accumulated, it became clear that this was far from the truth. Galaxies are not isolated in randomness. They form intricate, interconnected structures spanning hundreds of millions of light-years. This vast filamentary network is what scientists now call the cosmic web. The first hints of these large-scale patterns came from surveys in the mid-20th century. Astronomers recorded galaxy positions on photographic plates, a slow process. In the 1,970 seconds, Margaret Geller and John Huckra used spectroscopic measurements to determine redshifts and distances, plotting thousands of galaxies in 3 dimensions. Their maps showed galaxies aligned along filaments stretching hundreds of millions of light-years, intersecting at dense nodes to form clusters. Between filaments were vast voids, spanning tens to hundreds of millions of light-years and largely empty of visible matter. The network was named the cosmic web because of its resemblance to a spider's web. The cosmic web formed under the influence of gravity over billions of years. In the early universe, matter density was nearly uniform. Tiny fluctuations in density, visible today in the cosmic microwave background as temperature variations of 1 part in 100,000, served as seeds for large-scale structure. Denser regions attracted surrounding matter, forming dark matter halos. Gas followed these gravitational gradients, cooling and condensing to form the earliest stars and galaxies. Over time, gravity organized galaxies into filaments and sheets, leaving vast regions nearly devoid of luminous matter, known as cosmic voids. By the turn of the 21st century, large-scale surveys mapped the cosmic web in detail. The Sloan Digital Sky Survey, or SDSS, launched in 2000, catalogued over 3 million galaxies across roughly 1/3 of the sky. Its data revealed filaments forming an interlinked network, connecting clusters, superclusters, and galactic walls. The Sloan Great Wall is a filament extending more than 1.3 billion light-years, about 1/10 of the observable universe's diameter, making it one of the largest known structures. Filaments are dynamic, representing the flow of matter influenced by cosmic expansion, dark matter, and gravity. Dark matter is the invisible scaffolding of the cosmic web. Comprising roughly 85% of the universe's total matter content, it neither emits nor absorbs light, yet exerts gravitational influence on galaxies and intergalactic gas. Simulations show that galaxies form along dense filaments of dark matter, tracing its hidden contours. Observations of galaxy rotation curves, gravitational lensing, and cosmic microwave background anisotropies all confirm dark matter's role as the dominant mass component shaping the universe. Without it, filaments would be weaker, voids less pronounced, and galaxy formations significantly delayed. Clusters of galaxies occupy the nodes where filaments converge. Some clusters, such as Virgo, Coma, and Fornax, contain thousands of galaxies bound together by gravity. Within these dense environments, galaxies interact frequently, exchanging stars, gas, and occasionally merging entirely. The most massive galaxies in cluster cores are often elliptical galaxies, products of repeated mergers over billions of years. Surrounding them, the intracluster medium, a hot, X-ray emitting plasma, reaches temperatures of tens of millions of degrees, detectable by space-based X-ray observatories like Chandra and XMM Newton. This gas contains more mass than the galaxies themselves, further demonstrating the complexity of cluster environments. Between filaments and clusters lies the intergalactic medium, or IGM, a diffuse, nearly invisible sea of gas permeating the cosmic web. Though tenuous, with densities of only a few atoms per cubic meter, the IGM contains the majority of ordinary baryonic matter in the universe. Astronomers study it by observing distant quasars, supermassive black holes, actively accreting matter. As quasar light passes through intergalactic gas, it produces absorption lines, revealing the composition, temperature, and motion of the IGM. This interaction is crucial. Galaxies draw material from filaments, fueling star formation, recycling elements forged in supernovae, and enriching the intergalactic medium with heavier atoms like carbon, oxygen, and nitrogen. The cosmic web evolves over time. Cosmological simulations, such as the Illustris and Eagle projects, model billions of years of evolution, following gravitational collapse of dark matter and gas hydrodynamics. Simulations show filaments thickening, clusters growing, voids expanding, and galaxies merging along preferred directions. Filaments channel matter into clusters and influence galaxy morphology. Observations of galaxy alignments and cluster dynamics confirm that these simulated patterns match observed structures. Observations with instruments such as the Atacama Large Millimeter, Submillimeter Array, or ALMA detect cold molecular gas flowing along filaments, mapping material that forms stars. The James Webb Space Telescope, observing infrared wavelengths, detects galaxies forming a few 100 million years after the Big Bang. These observations reveal proto-galaxies a few thousand light-years across, embedded in filaments that evolve into larger spiral or elliptical galaxies. Dwarf galaxies trace filaments, populate voids, and contribute to chemical enrichment of intergalactic space. Interactions with larger galaxies can trigger star formation and affect cluster growth over billions of years. Mapping the cosmic web provides information about the distribution of dark matter, the influence of dark energy on cosmic expansion, and the timeline of structure formation. Measuring the shapes and orientations of filaments and clusters allows astronomers to constrain the equation of state of dark energy. The growth of large-scale structure over time is also used to test models of gravity, including modified Newtonian dynamics and general relativistic extensions. Gas streams along filaments, feeding galaxies and sustaining star formation over cosmic time. In massive clusters, interactions can strip gas from galaxies, depositing it into the intracluster medium, which becomes material for future star formation. These processes, occurring over hundreds of millions to billions of years, affect galactic evolution and the growth of supermassive black holes at galactic centers. Galaxies form along filaments, accumulating clusters, and leave voids behind. Observations and simulations show that the largest structures in the universe arise from the physics of the Big Bang, shaped by dark matter, gas dynamics, and energy flows across space and time. Tracing filaments backward in time allows researchers to identify the sites of the first galaxies and star-forming regions. Observations of these primordial structures provide information on how galaxies assembled their mass, how supermassive black holes formed, and how chemical enrichment began. Galaxies at dawn, the first lights of the universe. Before the universe as we know it emerged, space was a dark, almost featureless expanse, filled primarily with hydrogen and helium gas. For the first several hundred million years after the Big Bang, there were no stars, no galaxies, and no light, in the sense we recognize today, a period astronomers refer to as the Cosmic Dark Ages. The cosmos was expanding and cooling, while gravity quietly began organizing the primordial gas into the structures that would eventually ignite the first stars. The first galaxies appeared during the epoch known as Cosmic Dawn, roughly between 200 and 400 million years after the Big Bang. These early galaxies were minuscule by today's standards, often hosting only a few million stars compared to the Milky Way's roughly 250 billion. Yet, they played an outsized role in cosmic evolution. Their ultraviolet light initiated cosmic reionization, a fundamental process that transformed the universe from an opaque hydrogen fog into the transparent cosmos we see today. Without these first luminous systems, the universe would have remained shrouded in darkness for billions of years. Our understanding of these primordial galaxies has grown dramatically with the advent of advanced infrared telescopes. The James Webb Space Telescope, or JWST, launched in December 2021, has been transformative. Observing at wavelengths from 0.6 to 28 microns, JWST can detect photons that have traveled more than 13 billion years, capturing light emitted when the universe was less than 5% of its current age. Each photon carries information about the stars, gas, and dust in these galaxies, as well as the elements synthesized in the first supernovae. Complementary observations by the Hubble Space Telescope and ALMA reveal cold gas reservoirs and dust structures that fuel star formation in these nascent galaxies. Early galaxies were irregular and clumpy, with rapid, turbulent star formation. Star formation rates reach tens to hundreds of solar masses per year. Massive stars in these galaxies lived for only a few million years. Supernova explosions injected energy and heavy elements such as carbon, oxygen, and iron into the surrounding gas, contributing to subsequent generations of stars and chemical enrichment. Initially, the universe's hydrogen atoms were neutral, absorbing most ultraviolet light. Population 3 stars in early galaxies emitted ultraviolet photons that ionized surrounding hydrogen, creating bubbles of ionized gas. Over several hundred million years, these bubbles expanded and merged, completing reionization. Observations of the Gunn-Peterson trough in quasar spectra indicate that by roughly 1 billion years after the Big Bang, most of the intergalactic medium had become ionized. Chemically, these galaxies were remarkably simple. Their primordial composition consisted almost entirely of hydrogen and helium, with trace lithium. Elements heavier than helium, referred to as metals in astronomical parlance, were forged in the cores of population 3 stars and dispersed through supernovae. These early enrichment events were pivotal. They provided the raw material for more complex stellar populations, as well as for the formation of rocky planets. Observations of extremely metal-poor stars in the Milky Way's halo, some containing less than 1/10,000th the solar abundance of iron, offer fossil evidence of this earliest chemical evolution. Simulations provide a complementary lens on this era. Projects such as Blue Tides and Renaissance track the formation of galaxies in cosmological volumes exceeding 500 million light-years across, resolving individual dark matter halos down to masses of 10-7 solar masses. These models reveal that gas accreted into these halos along filaments of the cosmic web, cooled and ignited star formation. Mergers between small protogalaxies were frequent, driving rapid growth and shaping the hierarchical structure that defines the universe. Observations increasingly confirm these predictions. JWST has detected galaxies at redshifts of Z is approximately equal to 13-14, corresponding to just 300-350 million years after the Big Bang, some with stellar masses exceeding 10, 9 solar masses far larger than traditional models had predicted for such early times. Detecting these faint galaxies is a formidable challenge. Gravitational lensing has become an essential tool. Massive foreground galaxy clusters warp spacetime, magnifying the light from distant background galaxies. Using this natural telescope effect, astronomers have observed galaxies that would otherwise remain invisible, allowing detailed studies of their star formation, sizes, and internal structures. In some cases, lensing reveals multiple clumps of stars within a single early galaxy, suggesting active regions of star formation and ongoing mergers. Many early galaxies formed in protoclusters, small groups that evolved into massive clusters such as Virgo or Coma. Interactions and collisions among these galaxies triggered starbursts, redistributed gas, and contributed to chemical enrichment. Observations of early galaxies trace the transition from a neutral to an ionized universe and the formation of stars, galaxies, and clusters. These data help document the sequence of galaxy formation from protogalaxies to larger spirals and ellipticals. Modern observations are also revealing surprises that challenge conventional theory. JWST has identified early galaxies forming stars at astonishing rates, sometimes exceeding 100 solar masses per year, in regions less than a few thousand light-years across. Some appear surprisingly massive and well-structured for their age, suggesting that early galactic growth was faster and more efficient than previously thought. These discoveries are reshaping models of galaxy formation and feedback, illustrating that the universe's first lights were both vigorous and complex. The shapes of the cosmos, spirals, ellipticals, and irregulars. As the universe evolved beyond its first billion years, galaxies multiplied, diversified, and began to exhibit distinct structural forms. By observing galaxies across vast cosmic distances, astronomers recognized repeating patterns in shape, size, and composition. These forms, spirals, ellipticals, and irregulars, are not merely aesthetic. They encode the histories, environments, and physical processes that shaped each galaxy. Spiral galaxies are perhaps the most iconic and visually striking. Characterized by flat, rotating disks and winding arms, spirals host both young, luminous stars in their arms and older, stellar populations in their central bulges. The Milky Way is a barred spiral, with a central bar stretching roughly 27,000 light-years, and spiral arms extending outward across more than 100,000 light-years. Other well-known spirals include M81 Bode's Galaxy and NGC 1300, each displaying bright, well-defined arms shaped by density waves propagating through their disks. These waves compress interstellar gas, triggering bursts of star formation. In the Milky Way, the spiral arms host star-forming regions such as the Orion Nebula and open clusters like the Pleiades, illustrating ongoing cycles of stellar birth. The internal structure of spiral galaxies is layered. The bulge, containing older stars and relatively little gas, dominates the central gravitational potential. The surrounding disk, rich in gas and dust, is the primary site of star formation. Farther out, a faint halo of old stars and globular clusters extends tens of thousands of light-years, embedded within a massive dark matter halo that stabilizes the galaxy's rotation. Spiral galaxies contain supernova remnants, molecular clouds, and vast nebulae, which indicate ongoing processes of stellar evolution. Elliptical galaxies, in contrast, exhibit smooth, featureless shapes ranging from nearly spherical classified as E0 to highly elongated E7. They contain older, redder stars with little remaining gas or dust, indicating that star formation largely ceased billions of years ago. Unlike spirals, stars in ellipticals move in random orbits, creating a rounded spheroidal appearance. Many ellipticals form through galactic mergers, where two or more galaxies collide and coalesce. These events disrupt disks, redistribute stars, and can trigger brief starbursts before gas is exhausted. Some ellipticals are truly massive. Central cluster galaxies, such as Messier 87 or M87 in the Virgo cluster, contain hundreds of billions of stars and host supermassive black holes exceeding 6.5 billion solar masses. Observations of ellipticals using the Hubble Space Telescope and VLT, or Very Large Telescope, reveal metallicity gradients, showing that their inner regions are often enriched with heavier elements, evidence of early intense star formation. Irregular galaxies defy neat classification. They are typically small, low mass, and chaotic, often shaped by tidal interactions or past mergers. The large and small Magellanic Clouds, satellite galaxies of the Milky Way, are classic examples of irregular systems. Their asymmetric distributions of gas and stars, along with active star formation, produce massive stars and supernovae that enrich the intergalactic medium with elements like carbon and oxygen. Spirals can transform into ellipticals through repeated mergers, while tidal interactions can distort spirals into irregulars. Even within a single galaxy, internal processes reshape structure over time. Gas flows inward to feed central black holes, bars form and dissolve, and star formation migrates outward through spiral arms. Observing these changes across the electromagnetic spectrum, optical, infrared, radio, and X-ray, allows astronomers to track both the visible stars and the invisible dark matter that governs motion and stability. Colors and spectra further reveal the physical state of galaxies. Spiral arms appear blue due to young hot stars, while elliptical galaxies glow red from older stellar populations. Spectroscopic measurements of metallicity, the abundance of elements heavier than helium, trace generations of star formation. For instance, inner regions of spirals often show metallicities 2-3 times higher than their outer disks, reflecting concentrated star formation in the past. Even irregular galaxies exhibit pockets of enrichment, highlighting localized chemical evolution influenced by massive stars and supernovae. Galaxy interactions produce spectacular features. Tidal tails, long streams of stars and gas pulled by gravitational forces, are evidence of close encounters. The antennae galaxies NGC 4038 over 4039 provide a vivid example. Colliding disks trigger massive starbursts while stretching stars into extended tails hundreds of thousands of light-years long. Similarly, NGC 7252, sometimes called the Atoms for Peace galaxy, is a merger remnant showing complex loops of stars and gas, illustrating how collisions remodel galactic structure over hundreds of millions of years. Morphology also provides indirect evidence of dark matter. Rotation curves of spiral galaxies, first systematically measured by Vera Rubin in the 1970 seconds, show that stars in the outer disk rotate faster than expected based solely on visible matter. This discrepancy points to massive dark matter halos surrounding galaxies, governing not only spiral dynamics but also the shapes of ellipticals and irregulars. Modern surveys like SDSS map tens of thousands of galaxies, confirming the interplay between dark matter, baryonic matter, and cosmic environment in shaping morphology. The environment profoundly influences galactic shape. Spirals dominate low-density regions, such as the local group, where interactions are infrequent. Ellipticals are common in dense galaxy clusters, where repeated collisions build massive spheroids. Irregulars appear in evolving regions or as satellites of larger galaxies, showing how tidal forces and accretion shape evolution. The Milky Way, inside our galactic home. The Milky Way is the galaxy we inhabit, a sprawling spiral system spanning roughly 100,000 to 120,000 light-years and containing more than 200 billion stars. From our vantage point within the disk, however, visualizing its full structure is a complex challenge. astronomers rely on multi-wavelength observations to piece together its three-dimensional form. Optical telescopes, like the Hubble Space Telescope, capture starlight. Infrared instruments, such as Spitzer and WISE, penetrate dense dust clouds. Radio arrays, including the Very Large Array, or VLA, map cold hydrogen gas. Even X-ray observatories, like Chandra, and gamma-ray detectors, like Fermi, reveal high-energy processes near supernova remnants and the central black hole. Together, these tools allow scientists to study stars, gas, dust, and the unseen dark matter shaping the galaxy. At the center lies the galactic bulge, a dense, roughly spherical region dominated by older, reddish stars. Spanning about 10,000 light-years, the bulge contains stars moving in randomized orbits, contrasting with the organized rotation of the disk. Anchoring this mass is Sagittarius A star, a supermassive black hole approximately 4 million times the mass of the Sun. Stars near this black hole orbit at astonishing speeds. Some complete full orbits in mere decades. Observing these motions has provided the clearest evidence for the existence of supermassive black holes in galactic centers. Radiating outward, the galactic disk forms a flattened plane containing the majority of the Milky Way's stars, gas, and dust. The disk is threaded with spiral arms that Perseus, Sagittarius, Scutum Centaurus, and Orion arm, the last of which hosts the solar system. Spiral arms are not permanent features. They are density waves moving through the disk, compressing gas and igniting bursts of star formation. Ultraviolet and H-alpha emissions highlight regions of active stellar birth, including the Carina Nebula, the Lagoon Nebula M8, and the Eagle Nebula, home to the iconic Pillars of Creation. These nebulae illuminate how young, massive O and B-type stars sculpt the surrounding gas, creating spectacular formations visible across thousands of light-years. Embedded within the disk are molecular clouds, cold, dense regions, largely composed of molecular hydrogen. Clouds like the Orion Molecular Cloud Complex, or NGC 3603, can span tens to hundreds of light-years, serving as stellar nurseries. Inside these clouds, pockets of gas collapse under gravity to form protostars, which ignite nuclear fusion after millions of years. Star clusters often form together and gradually disperse, leaving behind both solitary stars and remnants of the parent molecular cloud. Supernovae, such as SN 1987A, inject energy and heavier elements carbon, oxygen, and iron back into the interstellar medium, enriching subsequent generations of stars and shaping the chemical evolution of the galaxy. Encasing the disk is the galactic halo, a diffuse, roughly spherical region populated by older stars, globular clusters, and dark matter. Globular clusters, such as M13 in Hercules or Omega Centauri, contain some of the oldest known stars, often exceeding 12 billion years in age. The halo also holds vast amounts of dark matter, which does not emit light but dominates the galaxy's gravitational mass. The presence of dark matter explains why stars in the outer disk orbit faster than visible matter alone would allow, ensuring the galaxy's stability and shaping the overall structure. The Milky Way's interstellar medium is highly dynamic and exists in multiple phases. Cold molecular clouds range from 10 to 50 K. Warmer neutral hydrogen reaches around 6,000 to 10,000 K, and ionized regions heated by supernovae can soar to 110 million K. Dust, though accounting for only about 1% of the interstellar mass, plays a vital role in star formation by shielding gas from ultraviolet radiation. Observations show that interstellar turbulence, shock waves, and magnetic fields all contribute to cloud collapse, filament formation, and subsequent star birth. The galaxy rotates as a complex system, With stars orbiting the center at roughly 220 kilometers per second, inner stars complete revolutions in tens of millions of years, while stars in the outer disk, such as the Sun, take approximately 225–250 million years to complete one orbit, a period sometimes called a galactic year. Differential rotation stretches spiral arms and redistributes gas and stars, influencing the location of star clusters and the formation of new spiral features. The Milky Way is not an isolated system. It interacts gravitationally with satellite galaxies, including the Large and Small Magellanic Clouds, and more than 50 known dwarf galaxies. Tidal interactions generate stellar streams, such as the Sagittarius stream, which wraps nearly twice around the galaxy, and the Orphan stream, remnants of disrupted satellites. These features provide evidence of the Milky Way's accretion of smaller galaxies and its growth through mergers over billions of years. Observations across the electromagnetic spectrum are essential for revealing the full structure of the Milky Way. Radio telescopes trace neutral hydrogen and molecular clouds invisible in optical light. Infrared instruments penetrate dust-obscured regions, uncovering hidden stellar populations near the galactic center. X-ray and gamma-ray detectors reveal energetic phenomena like supernova remnants, neutron stars, and high-energy emissions around Sagittarius A star. By combining data from all these sources, astronomers can reconstruct a detailed three-dimensional model of the galaxy's structure, composition, and evolution. The Milky Way also displays systematic chemical gradients. Metallicity, the abundance of elements heavier than helium, varies with location and age. Older halo stars formed when the universe had few heavy elements, and thus show low metallicity, while younger disk stars have higher metallicity due to the cumulative effects of stellar nucleosynthesis over billions of years. The thin disk exhibits higher metallicity than the thick disk, indicating differences in the sequence of element formation. Finally, the Milky Way exists within the local group, a gravitationally bound collection of over 50 galaxies. Interactions among these galaxies influence dynamics, morphology, and evolution. A future collision with the Andromeda Galaxy M31 is expected in roughly 4.5 billion years. This encounter will likely merge the two galaxies into a massive elliptical galaxy, redistributing stars, gas, and dark matter. The local group, our neighborhood of galaxies. Beyond the spiral arms of the Milky Way lies a cosmic neighborhood of remarkable complexity. The local group, a gravitationally bound collection of more than 50 galaxies spanning roughly 10 million light-years. This assortment of galaxies includes massive spirals, smaller dwarf systems, and faint irregular galaxies, offering a unique laboratory for studying galactic evolution up close. Because the local group is both nearby and sufficiently diverse, it allows astronomers to investigate the interplay of gravity, dark matter, and stellar populations on scales impossible to resolve in more distant systems. At the core of the local group are its two largest members, the Milky Way and the Andromeda Galaxy. Andromeda, slightly larger than the Milky Way, extends roughly 220,000 light-years across and contains over 1 trillion stars. Its prominent bulge, disk, and halo are comparable to the Milky Way's but exhibit distinct stellar streams, such as the giant stellar stream, which provide evidence of past mergers with smaller galaxies. Like the Milky Way, Andromeda hosts a supermassive black hole at its center, estimated at 140 million solar masses, more than 30 times the mass of Sagittarius A star. Detailed surveys with telescopes such as Hubble and Keck have mapped Andromeda's disk and halo with unprecedented precision, revealing star clusters, gas filaments, and faint satellite companions. The Triangulum Galaxy, or M33, is another notable spiral, smaller than both Andromeda and the Milky Way, spanning roughly 60,000 light-years. Its well-defined spiral arms contain luminous HI regions, such as NGC 604, one of the largest star-forming regions in the local group, which alone spans 1,500 light-years and contains thousands of young, hot stars. Unlike Andromeda and the Milky Way, M33 is relatively isolated, providing astronomers with a laboratory to study star formation and spiral structure in a less disturbed environment. Its disk also exhibits subtle warping, likely due to past interactions with M31 or nearby dwarf galaxies. Surrounding these dominant spirals is a swarm of dwarf galaxies, far more numerous than their larger neighbours. These dwarfs include spheroidal, irregular, and compact elliptical types, many dominated by dark matter. Some, like the Large Magellanic Cloud, or LMC, and Small Magellanic Cloud, or SMC, are visible to the naked eye from the southern hemisphere, while others, such as the Sexton's Dwarf, are detectable only through deep imaging or stellar motions. Many dwarf galaxies orbit larger galaxies, undergoing tidal interactions, stripping, and mergers that transfer stars, gas, and angular momentum to their hosts. The Sagittarius dwarf spheroidal galaxy is currently being absorbed by the Milky Way, with its stars stretched into elongated tidal streams, wrapping multiple times around the galaxy. The Orphan Stream, another tidal feature, shows similar processes occurring with smaller satellites. Observations of these streams provide data on the accretion history of the Milky Way and Andromeda. The dynamics of the local group are governed by a delicate balance between mutual gravitational attraction and cosmic expansion. While galaxies within the group remain gravitationally bound, the universe's expansion dominates at larger scales. Precise measurements of velocities using the Hubble Space Telescope, Gaia, and ground-based observatories reveal complex orbital patterns. Some galaxies, like M32 and M110, are approaching Andromeda, while others maintain stable orbits around the group's barycenter. These motions provide estimates of the local group's total mass, which is roughly 2 × 10 to the power of 12 solar masses, most of which resides in dark matter halos. Galactic interactions within the local group influence evolution. Close encounters can warp disks, trigger starbursts, and redistribute gas and stars. Smaller systems may be entirely disrupted, while more massive spirals can cannibalize dwarfs, altering their structure. The anticipated collision between the Milky Way and Andromeda in about 4 billion years is expected to generate a massive elliptical galaxy with a chaotic central region, extensive tidal tails, and possibly new bursts of star formation triggered by compressing gas. The local group is part of the Virgo supercluster, a network of galaxy groups and clusters spanning over 110 million light-years. Its proximity allows detailed mapping of stellar populations, gas content, and metallicity gradients, which can be compared across galaxies of different masses and morphologies. Advances in deep imaging and wide-field surveys, including PanSTARRS, DES, or Dark Energy Survey, and the Sloan Digital Sky Survey, have revealed previously hidden members of the local group. Ultra-faint dwarf galaxies, some containing only a few thousand stars, have been discovered near the Milky Way and Andromeda. These systems are almost entirely dark matter, with stellar to total mass ratios sometimes below 0.1%. Chemical composition across local group galaxies varies widely. Massive spirals like the Milky Way and Andromeda display a broad range of metallicities from Phi is approximately equal to -0.5 inches. The thin disk to Phi is approximately equal to -2. 0 inches, the halo reflecting multiple generations of star formation. Dwarf galaxies, in contrast, are often metal poor, with Phi as low as -2.5, indicating slower star formation and less enrichment from supernovae. The local group also provides insight into the distribution of dark matter. Observations of dwarf galaxy orbits, halo stellar motions, and tidal streams indicate that dark matter dominates the gravitational landscape. For example, the LMC and SMC are surrounded by extended dark matter halos several times larger than their visible disks. Studies of these structures test cosmological models, particularly predictions from WCDM or lambda-cold dark matter theory, which posits that galaxies form hierarchically within massive dark matter halos. Cosmic encounters. When galaxies collide. The universe is far from a static expanse of isolated galaxies. Across billions of years, galaxies interact, pass close to one another, and often collide in spectacular cosmic events. These galactic collisions are complex gravitational encounters that reshape the structure, star formation, and evolution of galaxies on immense scales. Despite the vast distances between individual stars, which usually prevent direct collisions, the gravitational effects of these encounters ripple through entire galactic systems, producing dramatic visual and physical transformations. Collisions unfold over hundreds of millions to billions of years. As galaxies approach, tidal forces stretch stars, gas, and dark matter into elongated streams, forming intricate tidal tails. Some of these tails extend over several 100,000 light-years. One of the most famous examples is the antennae galaxies NGC 4038, NGC 4039, where overlapping disks and twin tails reveal a turbulent merger in progress. Observations with the Hubble Space Telescope show thousands of bright star clusters forming within these tails, demonstrating the direct link between tidal forces and star formation. Starbursts are a hallmark of galaxy collisions. When interstellar gas clouds are compressed during encounters, waves of star formation ignite, producing massive, short-lived stars that emit intense ultraviolet radiation. These stars quickly end their lives as supernovae, enriching surrounding gas with heavier elements, such as oxygen, carbon, and iron. In some extreme cases, star formation rates can increase by factors of 10^100 compared to isolated galaxies. As observed in systems like M82, the Cigar Galaxy, where a central starburst has produced thousands of young, massive stars. Collisions also influence galactic nuclei. Supermassive black holes, typically found in galactic centers, can be driven together during mergers. As they orbit one another, they emit gravitational waves, ripples in spacetime first predicted by Einstein and now observed by facilities like LIGO and Virgo. When the black holes eventually coalesce, the resulting energy release can exceed the combined luminosity of entire galaxies, affecting the surrounding gas and sometimes triggering further star formation. The nature of a collision depends on the masses and structures of the galaxies involved. Major mergers, involving galaxies of roughly equal mass, can destroy original disk structures, producing massive elliptical galaxies. These mergers are often chaotic, with stars redistributed into spheroidal orbits and gas funneled towards central regions, fueling black hole growth and starbursts. In contrast, minor mergers, where a small galaxy interacts with a much larger one, typically leave the primary galaxy's structure mostly intact while stripping stars, gas, and dark matter from the smaller companion. Observations of the Sagittarius dwarf galaxy being absorbed by the Milky Way illustrate a minor merger in action, with tidal debris forming elongated stellar streams spanning tens of thousands of light-years. Irregular galaxies frequently display the scars of past collisions. Chaotic shapes, off-center star formation, and patchy distributions of gas are common, as seen in galaxies like NGC 4049 and IC10. Astronomers use these systems to model the timing, scale, and consequences of past galactic encounters, and to document galaxy morphologies. Galaxy collisions redistribute stars, gas, and dust, trigger bursts of star formation, feed central black holes, and mix stellar populations. Nearby collisions, such as the Mice galaxies NGC 4000, 676, and NGC 7252, are observed to study the physics of galaxy formation. Gravitational simulations have revolutionized the understanding of these encounters. Supercomputers can model millions of particles representing stars, gas, and dark matter, reproducing tidal tails, bridges, and ring structures seen in observations. By varying parameters such as mass ratio, orbital angle, and relative velocity, astronomers can predict outcomes of mergers with remarkable precision. For instance, simulations of the anticipated Milky Way Andromeda collision, projected to occur in about 4 billion years, predict multiple close passes, tidal disruptions, and eventual coalescence into a massive elliptical galaxy, with a disturbed stellar halo extending over 1 million light-years. Collisions are also pivotal for star cluster formation. Dense clusters of newly formed stars often arise in interacting galaxies, some surviving as globular clusters for billions of years. The antennae galaxies, for example, host over 1,000 young clusters, many containing hundreds of thousands of stars. Studying these clusters allows astronomers to probe the initial conditions of star formation and the mechanisms that produce extremely massive and tightly bound stellar systems. The influence of collisions extends beyond visible matter. Dark matter halos, which envelop galaxies, interact gravitationally during mergers, shaping tidal features, disk stability, and the final structure of merged systems. Observations of tidal debris and stellar motions provide indirect maps of dark matter, helping constrain its distribution and role in governing cosmic structure. For example, simulations suggest that the halos of the Milky Way and Andromeda will interpenetrate during their future collision, influencing the motion of hundreds of billions of stars and the dynamics of resulting tidal tails. Collisions are not restricted to isolated pairs. In galaxy clusters, multiple interactions occur simultaneously, creating complex chains of mergers, tidal distortions, and sometimes galactic harassment. Central cluster galaxies, such as Messier 87 inches, the Virgo cluster, often become massive ellipticals formed through successive collisions and accretions, while smaller galaxies are stripped of stars and gas, producing a population of ultra-compact dwarfs. Each galactic collision reshapes structure, triggers chemical enrichment, and influences the growth of central black holes. Observations of collisions across environments from isolated pairs to dense clusters document the formation of spiral and elliptical galaxies and the redistribution of stars, gas, and dark matter over time. Supermassive black holes, engines of galactic evolution. At the center of nearly every massive galaxy resides a supermassive black hole, a gravitational titan whose mass ranges from millions to billions of times that of the Sunday. These enigmatic objects are not merely cosmic curiosities, they are dynamic engines that influence the structure and energy output of their host galaxies. Though invisible to direct observation, supermassive black holes reveal themselves through their dramatic effects on nearby stars, gas clouds, and even the large-scale morphology of entire galaxies. Observations of these effects allow astronomers to study galaxy formation, chemical enrichment, and energetic phenomena across the universe. The Milky Way's central black hole, Sagittarius A star, has a mass of roughly 4.1 million solar masses. It is surrounded by a dense cluster of stars known as the stars, whose orbits near the black hole reach velocities exceeding 7,500 kilometers per second. Using instruments such as the Very Large Telescope and the Keck Observatory, astronomers have tracked these stars with remarkable precision, confirming the black hole's mass and testing Einstein's theory of general relativity in extreme gravitational fields. Observations reveal phenomena such as gravitational redshift and orbital precession, providing unique laboratories for physics beyond Earth-based experiments. Sagittarius A star's quiet state contrasts with active galactic nuclei, but its gravitational influence extends over several light years, subtly shaping the motions of stars in the galactic core. Supermassive black holes exert their power most dramatically through accretion. Matter spiraling inward forms an accretion disk, where friction and gravitational forces heat the material to millions of degrees, emitting radiation across the electromagnetic spectrum. This energy can make the black hole the brightest object in its galaxy, producing phenomena collectively known as active galactic nuclei, or AGN. Among the most luminous AGN are quasars, which can outshine billions of stars combined. For instance, quasar ULAS J1342 plus 0928, observed at redshift Z equals 7.54, existed just 690 million years after the Big Bang, and contains a black hole of approximately 800 million solar masses. Observations of high redshift quasars provide constraints on models of early black hole growth and mass accumulation rates in the young universe. The influence of supermassive black holes extends beyond luminosity. AGN feedback regulates star formation by expelling gas from galactic centers via powerful winds and relativistic jets. In some cases, energy outputs reach 1046 ergs per second, enough to prevent the collapse of interstellar clouds and quench star formation over kiloparsec scales. Conversely, gas inflows during mergers can compress material in circumnuclear regions, triggering intense star formation. Observations indicate that the effect of black holes on star formation varies depending on local gas density, merger activity, and other environmental conditions. A striking feature of supermassive black holes is their tight correlation with the properties of their host galaxy bulges, encapsulated in the M-sigma relation. For example, the giant elliptical galaxy M87 harbors a 6.5 billion solar mass black hole, consistent with expectations from its bulge stellar velocity dispersion. This relationship suggests coevolution. As the galaxy's bulge grows, the central black hole accrues mass, maintaining a regulatory feedback loop. Galaxy mergers often accelerate this growth, funneling gas toward the nucleus and activating phases of AGN activity, which in turn influences star formation, chemical enrichment, and even the morphology of the resultant galaxy. Supermassive black holes also influence the large-scale structure of galaxies. In spirals, feedback from the black hole helps stabilize disks and influence spiral arm formation. In ellipticals, it contributes to quenching star formation, producing smooth, featureless structures dominated by old stars. During galactic mergers, black holes may form binary systems, orbiting each other and gradually losing energy through gravitational wave emission, eventually coalescing. Observatories such as LIGO and the upcoming LISA mission aim to detect these waves, providing measurements of black hole mass, spin, and dynamics. Black hole growth occurs through both steady accretion and episodic mergers. Accretion rates vary, sometimes reaching tens of solar masses per year during luminous quasar phases. Mergers, though less frequent, can add enormous mass quickly. Evidence of such events exists in dual AGN systems like NGC 6240, where two actively accreting black holes are separated by just 1,000 light-years. Over hundreds of millions of years, these black holes will merge, releasing energy equivalent to millions of supernovae and profoundly affecting the surrounding stellar population. These mergers contribute to the hierarchical growth of black holes, building some of the most massive known objects in the universe, such as the 21 billion solar mass black hole in the elliptical galaxy IC 1101. Detection techniques for supermassive black holes are multifaceted. In addition to monitoring stellar orbits and AGN emissions, astronomers employ X-ray telescopes to map high-energy radiation from accretion disks, radio arrays to trace relativistic jets, and water maser emissions to measure precise rotational velocities of molecular disks. The Event Horizon Telescope, or EHT, produced the first direct image of a black hole's shadow in M87, a milestone confirming decades of indirect evidence. Combined, these methods allow astronomers to survey black holes across a range of masses and distances, constructing a cosmic census that informs theories of galaxy evolution, feedback, and early universe conditions. The impact of supermassive black holes extends to chemical enrichment and stellar population evolution. Starbursts triggered by gas infall toward the nucleus produce massive stars that explode as supernovae, dispersing heavy elements into the interstellar medium. This metal-rich gas contributes to subsequent generations of stars and planetary systems, shaping the chemistry of galactic centers. Regions influenced by black hole-driven feedback often exhibit high metallicities, consistent with observed abundance patterns in bulge stars. Theoretical simulations have further illuminated the role of black holes in cosmic evolution. Projects such as Illustris, Eagle, and Horizon AGN model the growth of galaxies and their central black holes across billions of years, incorporating physics of gas dynamics, star formation, feedback, and mergers. These simulations show that without black holes, galaxies would overproduce stars and fail to match observed luminosity functions and morphologies. Simulation results indicate that including black holes in models reproduces observed galaxy properties and large-scale structure. Star nurseries. How stars shape galaxies. Galaxies are far from static. They are dynamic ecosystems in which new stars are continuously born, live out their lives, and recycle material back into the interstellar medium. These stellar birthplaces, often referred to as star nurseries, are dense regions of gas and dust where gravity triggers the collapse of matter into new stars. Studying these nurseries is crucial for understanding not only the life cycle of galaxies, but also the creation of chemical elements and the formation of planetary systems which may ultimately host life. The primary sites of star formation are giant molecular clouds, enormous conglomerates of cold molecular gas, composed predominantly of hydrogen H2, with helium making up about 25% of the mass, and trace amounts of heavier elements such as carbon, oxygen, nitrogen, and iron. These clouds can span tens to hundreds of light years, with some, like the Taurus molecular cloud, stretching over 450 light years and containing hundreds of thousands of solar masses of material. Denser regions within these clouds, known as cores, undergo gravitational collapse, gradually forming protostars that eventually ignite nuclear fusion. Infrared and radio observations are indispensable for studying these early stages because the dust within the clouds absorbs visible light, hiding the earliest phases of star formation from optical telescopes. Within the Milky Way, several star-forming regions provide examples of stellar nurseries. The Orion Molecular Cloud Complex, located approximately 1,350 light-years away, contains the Orion Nebula, or M42, home to more than 3,000 young stars, including massive O-type and B-type stars. At the nebula's heart lies the Trapezium cluster, whose ultraviolet radiation carves cavities into the surrounding gas while compressing nearby regions. Similarly, the Carina Nebula, roughly 7,500 light-years from Earth, contains the massive star Eta Carinae, estimated at over 100 solar masses, which produces strong winds and eruptions affecting its surrounding gas. Star formation is highly variable in both space and time. High-mass stars, typically 10 to 50 times the mass of the Sun, form rapidly and exhaust their fuel in just a few million years. Their explosive deaths, as supernovae, inject heavy elements, including iron, silicon, oxygen, and calcium, into the surrounding medium. In contrast, low-mass stars, like the Sun, evolve over billions of years. The chemical enrichment from massive stars increases the metallicity of subsequent stellar generations. Star clusters are a key product of molecular cloud collapse. Open clusters, such as the Pleiades or M45 and Hyades in the Taurus constellation, contain dozens to thousands of stars formed from the same molecular cloud. They are loosely bound gravitationally and gradually disperse over hundreds of millions of years, contributing stars to the galactic field. Globular clusters are densely packed spherical systems containing hundreds of thousands of stars, some of which are over 12 billion years old. Studying these clusters involves measuring star ages, metallicities, and dynamics. The galactic environment strongly influences star formation. Spiral arms act as density waves, compressing gas and dust as it orbits the galaxy, producing chains of star-forming regions along the arms. In the Milky Way's Sagittarius arm, numerous H2 regions host ongoing star formation at rates up to 2-3 solar masses per year. Elliptical galaxies show little to no active star formation, as most of their gas has been expelled by supernova-driven winds or heated to millions of degrees by prior active galactic nuclei. Star formation is also self-regulating. Protostars produce stellar winds and bipolar jets, which can disperse surrounding gas, halting the collapse of nearby cores. In some massive star-forming regions, winds from several O-type stars combine to form superbubbles, cavities tens of light-years across, which both trigger and suppress subsequent star formation. These processes involve interactions between gas, radiation, gravity, and magnetic fields. Technological advances have revolutionized the study of star nurseries. Infrared observatories like the James Webb Space Telescope and the Spitzer Space Telescope penetrate dense clouds to reveal embedded protostars, disks, and complex chemical structures. Radio interferometers, such as the Atacama Large Millimeter, Submillimeter Array, map gas and dust at subarc-second resolutions, revealing filaments, clumps, and cores where stars are forming. Observatories like SOFIA and Herschel Space Observatory have traced far infrared emissions from coal dust, enabling studies of star formation in both local and distant galaxies. These instruments together provide a near-complete view of the earliest stages of stellar evolution. Star-forming regions contribute to a galaxy's total luminosity, chemical enrichment, and mass redistribution. As stars evolve and die, their winds and supernovae recycle gas, altering the density, temperature, and composition of the interstellar medium. Star formation rates, or SFRs, vary widely. The Milky Way forms approximately 7-10 solar masses of stars per year, while starburst galaxies like M82, the Cigar Galaxy, form over 100 solar masses annually. In luminous infrared galaxies, or LIRGs, and ultraluminous infrared galaxies, or ULIRGs, SFRs can exceed 1,000 solar masses per year. Star formation is also closely tied to planet formation. Protoplanetary disks around young stars, composed of gas and dust, gradually coalesce into planets, asteroids, and comets. Observations of disks in regions such as Taurus, Ophiuchus, and the Orion Nebula reveal gaps, rings, and spiral arms, showing ongoing planet formation. Disk studies provide measurements of mass distribution, disk composition, and potential for forming terrestrial and giant planets. Molecular clouds collapse to form star clusters, with processes involving gravity, radiation, turbulence, and chemistry. Star formation replenishes interstellar material and contributes to galaxy evolution. Regions such as the Carina Nebula, Orion Molecular Cloud, and distant starburst galaxies contain active star-forming sites across the universe. Even in our own galaxy, roughly 7 new stars form each year, a rate similar to other spiral galaxies, such as M31, while starburst galaxies, like NGC 253, can form hundreds of stars annually in dense clusters. The life cycle of galaxies, growth, change, and decline. Galaxies are not eternal, static entities. They undergo a dynamic life cycle spanning billions of years. From their initial formation shortly after the Big Bang to their evolution through mergers, star formation, and eventual decline, galaxies exhibit complex behaviors driven by gravity, gas dynamics, stellar evolution, and interactions with their environment. Galaxies show connections among star formation, chemical enrichment, and structural changes over time. The earliest galaxies formed roughly 400–600 million years after the Big Bang, when primordial gas collapsed into the gravitational wells of dark matter halos. These halos, composed of an invisible form of matter, accounting for approximately 85% of the universe's mass, acted as scaffolds, attracting ordinary baryonic matter, including hydrogen, helium, and trace heavier elements. Gas cooling within these halos led to the formation of the first generations of stars, creating compact, irregular proto-galaxies. Observations with telescopes like the James Webb Space Telescope have revealed galaxies at redshifts exceeding Z=11, corresponding to less than 400 million years after the Big Bang, allowing astronomers to study the universe's earliest structures. These primitive galaxies were typically less than a few thousand light-years across, but exhibited intense star formation rates, sometimes exceeding 10 solar masses per year, far higher than expected given their small sizes. Galaxies grow through two primary mechanisms: accretion of gas and mergers with other galaxies. Gas accretion delivers the raw material needed for ongoing star formation, often through filamentary structures in the cosmic web, which funnel cold gas directly into galactic disks. Mergers, by contrast, physically reshape galaxies. Major mergers, where galaxies of similar mass collide, can transform spirals into massive ellipticals, trigger starburst activity, and redistribute stars and gas over tens of thousands of light-years. For instance, the Antennae galaxies NGC 4038 over 4039, located about 45 million light-years away, are currently undergoing a major merger, producing intense starburst regions that host young star clusters numbering in the tens of thousands. Minor mergers, where a large galaxy absorbs a smaller satellite, add stars gradually, create tidal streams, and sometimes supply fresh gas to fuel star formation in the host galaxy. The Milky Way itself is undergoing minor mergers, absorbing small satellites like the Sagittarius dwarf galaxy, whose tidal debris stretches across tens of thousands of light-years. Star formation within galaxies follows distinct patterns based on morphology and environment. Spiral galaxies, such as the Milky Way and M81, sustain ongoing star formation in their disks, producing a mix of hot, blue stars and older, redder populations. Star formation rates in spiral galaxies vary. The Milky Way averages roughly 710 solar masses per year, while massive spirals like M101 may reach 1520 solar masses per year. Elliptical galaxies, in contrast, often experience an initial burst of star formation that rapidly consumes available gas, leaving a population dominated by older stars. Irregular galaxies, including the Large and Small Magellanic Clouds, display chaotic, patchy star formation driven by interactions and local gas density variations. Environmental factors, such as tidal interactions and ram pressure stripping in clusters, further influence star formation rates. In the Virgo cluster, for example, ram pressure stripping removes cold gas from galaxies moving at several hundred kilometers per second through the hot intracluster medium, suppressing their star formation. Internal processes are equally critical to galactic evolution. Central supermassive black holes, ranging from millions to billions of solar masses, regulate star formation through energetic feedback. Active galactic nuclei can heat, expel, or redistribute gas, preventing excessive starburst activity. Stellar feedback from winds, supernovae, and radiation pressure similarly disperses gas, redistributing heavy elements and shaping the potential for future star formation. For example, NGC 1275 inches, the Perseus cluster exhibits both AGN-driven outflows and star formation in filamentary structures, showing simultaneous feedback and star formation activity. Chemical enrichment occurs through successive generations of stars, fusing hydrogen and helium into heavier elements, which are returned to the interstellar medium through supernova explosions and stellar winds. Over time, the metallicity of a galaxy increases, influencing the efficiency of star formation, the opacity of gas, and the likelihood of planet formation. Observations of metallicity gradients in galaxies reveal that central regions are often more enriched than outer disks. For instance, the Milky Way exhibits a metallicity gradient of approximately 0.06 dex per kiloparsec, with central stars containing roughly twice the heavy element abundance of stars near the Sunday. By analyzing the chemical composition of stars and gas, astronomers can reconstruct a galaxy's evolutionary history and distinguish between in situ star formation and accretion of external material. Galaxy morphology undergoes significant changes over billions of years. Spiral arms may become less distinct as gas is depleted or redistributed, while mergers can transform disks into spheroidal elliptical galaxies. Irregular galaxies often result from tidal disruptions or the accretion of gas-rich companions, while lenticular galaxies represent intermediate stages, featuring disk structures but little active star formation. These transformations reflect the underlying dynamics of stars, gas, dark matter, and black holes interacting over vast timescales. Observations of the Hubble Deep Field demonstrate that the fraction of irregular galaxies was higher in the early universe, supporting the view that mergers and interactions were more frequent during the first few billion years after the Big Bang. Galaxies in dense clusters experience accelerated transformation through mechanisms such as ram pressure stripping, galaxy harassment, and tidal interactions. In contrast, isolated galaxies evolve more gradually, often retaining their spiral structures and cold gas reservoirs for longer periods. Studies of the Coma cluster reveal that elliptical galaxies dominate the core, while spiral galaxies are more common in the periphery, highlighting the influence of the environment on morphology and star formation. Interactions with neighbors, as seen in the M81 group, can trigger star formation, create tidal bridges, and redistribute gas, showing how external and internal processes operate simultaneously. Gas reservoirs in aging galaxies diminish, star formation slows, and stellar populations redden. Spiral galaxies may lose distinct features, while massive ellipticals enter a quiescent phase, dominated by old stars and exhibiting minimal new star formation. The largest galaxies, such as NGC 4889 inches, the Coma cluster, may contain hundreds of billions of stars, yet show little evidence of ongoing star formation. Observations indicate that galaxies transition from blue, star-forming systems to red, quiescent ones over 1–2 billion years, reflecting the depletion of cold gas and the cumulative effects of feedback processes. Simulations of galactic evolution have become increasingly sophisticated. Projects such as Illustris TNG and Eagle model galaxies over billions of years, incorporating gravity, hydrodynamics, star formation, and feedback from black holes. These simulations reproduce the observed diversity of galaxy types, star formation histories, and chemical abundances, showing how different initial conditions and merger histories can produce spirals, ellipticals, lenticulars, and irregulars. By comparing simulated galaxies with observations, astronomers refine their understanding of the physical processes driving growth, transformation, and decline. Observational evidence of galactic life cycles spans both local and distant galaxies. Nearby galaxies, such as Andromeda and M33 or Triangulum, display mature structures shaped by mergers and star formation histories over billions of years. Distant galaxies observed at redshift Z is greater than 6 reveal compact, irregular shapes with extremely high star formation rates, representing early stages of evolution. Observations across cosmic time show connections between early starbursts and massive ellipticals observed today. The hidden builders, dwarf galaxies, and their galactic influence. Amid the vast, luminous, spiral, and elliptical galaxies that dominate the observable universe, there exists a population of much smaller, fainter galaxies known as dwarf galaxies. These galaxies act as building blocks for larger galaxies and contribute to the dynamics, chemical composition, and star formation histories of their surroundings. Dwarf galaxies are widespread and persist in a variety of cosmic environments, providing observable examples of hierarchical galaxy formation. Dwarf galaxies are remarkably diverse. Dwarf spheroidals, or DSFs, are diffuse, with little or no interstellar gas, and contain predominantly old stars. Examples include Draco, Ursa Minor, and Sculptor, each with stellar populations numbering between 10,000 and a few million stars. In contrast, dwarf irregulars, or DIRs, retain significant amounts of gas and exhibit ongoing star formation, such as the Large Magellanic Cloud and IC 1613, which actively form stars at rates of 0.1–0.3 solar masses per year. Ultra-compact dwarfs, or UCDs, are densely packed systems containing millions of stars in regions only a few hundred light-years across, often found near massive galaxy clusters like Fornax. Relative to a giant spiral such as the Milky Way, which hosts 200–400 billion stars, dwarf galaxies are significantly smaller but can contribute stars, gas, and dark matter to larger systems. Hierarchical galaxy formation models emphasize the central role of dwarf galaxies in cosmic assembly. Large galaxies grow over billions of years by accreting smaller systems. Dwarf galaxies provide stars, gas, and dark matter, fueling the growth of their massive hosts. Stellar streams in the Milky Way, including the Sagittarius Stream and the Orphan Stream, are remnants of disrupted dwarf galaxies, offering a direct record of past mergers. These streams stretch tens of thousands of light-years across the halo, mapping both the history of the Milky Way's assembly and the gravitational potential shaping it. Similar features are observed around Andromeda, where over 30 distinct stellar streams trace previous mergers with satellites such as M32 and NGC 205. The survival and evolution of dwarf galaxies are strongly influenced by the environment. Within galaxy clusters, they experience processes such as ram pressure stripping, where the hot intracluster medium removes gas from dwarfs, halting star formation and transforming irregulars into spheroidals. Observations in the Virgo cluster reveal that many dwarfs in the dense cluster core are gas-poor and quiescent, while those in the periphery retain gas and actively form stars. Isolated dwarfs, including WLM or Wolf-Lundmark-Melotte, can maintain star formation over billions of years, allowing astronomers to observe differences in evolution between low and high-density environments. Despite their faint appearance, dwarf galaxies often harbor significant dark matter halos, sometimes with dark to luminous mass ratios exceeding 100:1. These halos stabilize dwarfs against tidal disruption by more massive galaxies and allow them to survive for billions of years. The study of dwarf galaxies has been central to constraining the nature of dark matter. For instance, the velocity dispersion of stars in Sculptor and Fornax implies total masses of 10, 7, 10, 8 solar masses, vastly exceeding the stellar mass alone. Ultra-faint dwarfs, such as Segway 1 and Boots I, contain as few as a few thousand stars, yet appear embedded in massive dark matter halos, challenging conventional models of star formation efficiency. Dwarf galaxies play a critical role in chemical enrichment. Although small, their successive generations of stars produce metals that enrich the interstellar medium. When dwarfs merge with larger galaxies, they deliver these heavy elements to the host, contributing to the diversity of stellar metallicities observed in systems like the Milky Way. The Large Magellanic Cloud, for example, has a mean stellar metallicity of roughly 0.5 solar, while older stars in the Sagittarius dwarf reach as low as 0.02 solar. This process can result in observable metallicity gradients across galactic halos and disks. Starburst activity, while rare in dwarfs compared to spirals, can be intense relative to their size. Regions such as 30 Doradus or the Tarantula Nebula in the LMC produce hundreds of massive stars and several supernovae per million years, injecting energy and metals into the surrounding medium. Feedback processes from starbursts can drive gas outflows that extend tens of thousands of light-years from the dwarf galaxy, altering gas distribution during interactions with larger galaxies. Dwarf galaxies also offer a window into the early universe. Many nearby dwarfs resemble the primordial galaxies that formed shortly after the Big Bang, characterized by small size, low metallicity, and inefficient star formation. Observations of low metallicity dwarfs, such as IceWiki 18, indicate that star formation can proceed sporadically over billions of years, with bursts separated by long quiescent periods. These observational characteristics provide data for studying early galaxy formation and feedback processes. Satellite dwarf galaxies orbiting larger systems provide further insights. Their orbital dynamics serve as probes of the host galaxy's total mass, including dark matter. For the Milky Way, satellites such as Fornax, Leo I, and Carina reveal that the galaxy's total mass within 300 kpc exceeds 1.5 times 10, 12 solar masses. Tidal interactions between satellites and their hosts can induce star formation, distort dwarf morphology, and produce observable stellar streams. Some dwarf galaxies defy conventional expectations. Ultra-faint dwarfs, with absolute magnitudes fainter than 6, demonstrate that dark matter halos can exist with extremely inefficient star formation. These systems provide data for testing theoretical models, showing that stellar feedback, cosmic reionization, and environmental factors can prevent significant star formation, even in dark, matter-dominated halos. Dwarf galaxies are also critical to understanding the dynamics of galaxy clusters. In clusters such as Virgo and Coma, they are the most numerous types of galaxy, collectively contributing to the gravitational potential, intracluster medium enrichment, and overall structure. Observations indicate that dwarfs can account for up to 10–15% of the stellar mass in a cluster, despite their individual faintness. Their combined mass and distribution influence the motions of larger galaxies and the distribution of hot gas within the cluster. Cities of the cosmos, exploring galaxy clusters. Beyond individual galaxies lies a higher level of cosmic organization, galaxy clusters. These immense structures, gravitationally bound collections of hundreds to thousands of galaxies, represent some of the largest coherent formations in the universe. They are cosmic metropolises where interactions among galaxies, the interplay of dark matter, and the behavior of the hot intracluster medium influence their structural and dynamical properties. Galaxy clusters vary widely in size, density, and composition. Rich clusters, such as the Coma cluster, Abell 1656, host more than 1,000 galaxies within a region approximately 20 million light-years across, dominated by massive ellipticals in the core. In contrast, poor clusters, like the Fornax cluster, contain only a few dozen to several hundred galaxies with looser central concentrations. Cluster galaxies are not randomly distributed. They follow the cluster's gravitational potential, forming dense central regions and more diffuse outskirts populated by spiral galaxies, dwarf galaxies, and ultra-faint systems. Observations indicate that cluster cores can reach densities exceeding 1,000 galaxies per cubic megaparsec, while the outer regions may have fewer than 10 galaxies per cubic megaparsec, highlighting the stark environmental gradient within clusters. At the heart of most clusters lie the brightest cluster galaxies, or BCGs. These colossal ellipticals, including NGC 4000, 889 inches coma, and NGC 4874, contain trillions of stars and dominate the gravitational landscape of their host clusters. BCGs grow primarily through galactic cannibalism, merging with smaller galaxies and accreting stars and gas from their surroundings. Many BCGs harbour supermassive black holes exceeding 10 solar masses, whose energy output via active galactic nuclei can heat the surrounding gas, regulate star formation, and influence the dynamics of the intracluster medium. This feedback affects the temperature and density distribution of gas in cluster cores. The intracluster medium, or ICM, a hot, X-ray emitting plasma that permeates clusters, contains more mass than all the galaxies combined. Temperatures in the ICM typically range from 10 to 100 million Kelvin, while densities are extremely low, around 10-3 particles per cubic centimeter. The gas is enriched with elements such as oxygen, iron, and silicon, produced by billions of supernovae over the cluster's lifetime. The ICM is not passive. As galaxies move through it at velocities of up to 1,500 kilometers per second, they experience ram pressure stripping, losing cold gas, and halting star formation. This process transforms spiral galaxies into gas-poor, red ellipticals, particularly within the dense cores of clusters. Observations of jellyfish galaxies, which exhibit long tails of stripped gas, provide direct evidence of these environmental effects. Dark matter dominates the gravitational landscape of galaxy clusters. Measurements of galaxy velocities and gravitational lensing reveal that visible matter constitutes only 10–15% of a cluster's total mass, while the remainder is dark matter forming an extensive halo. For example, the Coma cluster's total mass is roughly 1.3 times 10^15 solar masses, with dark matter accounting for approximately 85–90%. This dark halo governs the motions of galaxies, the distribution of the ICM, and the growth of cluster substructures. Astronomers measure galaxy velocities and lensing effects to determine the distribution of dark matter within clusters. Interactions between galaxies in clusters are frequent and diverse. Close encounters can induce tidal distortions, generating stellar streams, bridges, and shells. Collisions can trigger starbursts, as seen in cluster mergers like Abell 2744 Pandora's cluster, or strip galaxies of their gas, quenching future star formation. These interactions influence the morphological composition of clusters, with elliptical galaxies dominating dense cores and spirals, or irregulars more prevalent at larger radii. Observations show fossil groups such as NGC 6482, dominated by a single massive elliptical galaxy and a faint surrounding population. Galaxy clusters are also sites of extreme astrophysical phenomena. Cluster mergers generate shock waves in the ICM, heating gas to tens of millions of degrees and producing turbulence observable in X-rays and radio frequencies. Magnetic fields, reaching microgauss levels, thread the ICM, guiding the motion of relativistic particles and influencing cosmic ray propagation. Radio halos and relics, such as those in Abell 2256, reveal the presence of relativistic electrons energized by cluster turbulence. These phenomena are studied through X-ray and radio observations to analyze plasma behavior under high temperature, low density conditions. Clusters grow hierarchically over time. Smaller groups of galaxies fall into larger clusters, and clusters themselves can merge to form superclusters. The Laniakea supercluster, home to the Milky Way, contains over 100,000 galaxies spread across 500 million light-years. Observations indicate that cluster mergers can release kinetic energies exceeding 10^64 ergs. These mergers can redistribute the ICM and dark matter and alter the dynamics of cluster galaxies. Observing clusters requires a multi-wavelength approach. Optical surveys, such as the Sloan Digital Sky Survey, map the distribution of galaxies, while X-ray observatories like Chandra and XMM Newton trace the hot ICM. Radio telescopes detect synchrotron emission from relativistic electrons, and millimeter wave observatories, including the Atacama Cosmology Telescope and South Pole Telescope, measure the Sunyaev-Zeldovich effect, revealing the thermal properties of cluster gas. Infrared observations with Spitzer and JWST detect star formation hidden by dust in cluster galaxies. These observations provide three-dimensional data on the positions of galaxies, gas density, and dark matter distribution. The abundance, mass distribution, and evolution of clusters are sensitive to the underlying properties of the universe, including dark energy, matter density, and the amplitude of primordial density fluctuations. By counting clusters at varying redshifts and analyzing their structure, scientists can constrain the rate of cosmic expansion and test predictions of the WCDM model. For instance, observations of massive clusters at high redshift, such as SPT CLJ 2000, 106-5844, reveal constraints on early cluster formation and the growth of large-scale structure. Dwarf galaxies, the most numerous members, trace the cluster's gravitational potential and record its assembly history. Studies of dwarf populations in the Virgo cluster reveal thousands of faint spheroidals and irregulars, whose interactions with larger galaxies contribute to tidal debris and enrich the ICM with metals. The space between. The intergalactic medium revealed. While galaxies and clusters dominate the visible universe, the vast spaces between them, once assumed to be empty, are filled with a diffuse, elusive substance known as the intergalactic medium. Far from being a vacuum, the IGM contains the majority of the universe's ordinary matter, or baryons, forming a cosmic reservoir from which galaxies draw gas to fuel star formation, and into which they deposit energy, heavy elements, and magnetic fields. Observations of quasar absorption lines, X-ray emission, and cosmological simulations provide direct measurements of the IGM's density, temperature, and composition across different cosmic epochs. The IGM is composed predominantly of hydrogen, 75%, and helium, 25%, with trace amounts of heavier elements such as carbon, oxygen, and iron, expelled by galaxies through supernovae and galactic winds. Its density is astonishingly low, on the order of 110 atoms per cubic meter. Yet it stretches across millions of light-years, forming an intricate network of filaments, sheets, and voids. Collectively, these structures constitute the cosmic web, the gravitational scaffolding that organizes matter on scales of hundreds of millions of light-years, connecting clusters, groups, and isolated galaxies in a single dynamic system. Detecting the IGM is challenging because of its tenuous nature. One of the most powerful techniques is absorption line spectroscopy of distant quasars. Quasars' luminous, active galactic nuclei, powered by supermassive black holes, emit intense radiation that passes through intergalactic gas, producing characteristic absorption features known as the Lyman alpha forest. Each absorption line corresponds to a cloud of neutral hydrogen along the line of sight, revealing its density, temperature, and velocity. Surveys such as the Sloan Digital Sky Survey and instruments like HIAS on Keck have mapped thousands of quasar sightlines, enabling the reconstruction of the IGM's three-dimensional structure across billions of light-years. The state of the IGM is far from uniform. The warm-hot intergalactic medium, or WIM, with temperatures between 10.5 and 10.7 kelvins, contains a large fraction of baryonic matter and is largely ionized, making it difficult to detect directly. X-ray observatories such as Chandra, XMM Newton, and the upcoming Athena mission have identified WIM filaments in emission and absorption, particularly along the outskirts of galaxy clusters. Cooler regions, meanwhile, host neutral hydrogen clouds that can later collapse to form dwarf galaxies or replenish existing galactic reservoirs. These clouds, sometimes observed as damped Lyman alpha systems, can contain gas masses up to 10 solar masses, rivaling the largest galaxies in terms of raw material for star formation. The IGM and galaxies exist in a continuous feedback loop. Galaxies draw gas from the IGM to fuel star formation, while energetic events such as supernova explosions, stellar winds, and outflows from supermassive black holes inject energy, momentum, and metals into intergalactic space. Observations of metal absorption lines, including C4, O6, and SI4, indicate that the IGM has been enriched to approximately 1/10% of the solar metallicity, even in regions hundreds of millions of light-years from the nearest galaxy. This chemical evolution provides a record of cosmic star formation and the dispersal of elements over billions of years. Interactions between galaxies and the IGM are particularly pronounced in galaxy clusters and groups. As galaxies move through the hot intracluster medium at speeds of 1,000–1,500 km per second, ram pressure stripping can remove cold gas from galactic disks, enriching the surrounding IGM with metals and altering the galaxy's evolutionary path. Filaments linking clusters act as conduits for both gas inflow and galaxy migration, funneling material into dense regions of the cosmic web. Studies of the Sculptor Wall and Coma Abel 1367 filament reveal that these intergalactic highways can span tens of megaparsecs, directly feeding clusters with both gas and smaller galaxies over cosmological timescales. The IGM also holds critical clues to the universe's earliest epochs. Following the reionization era, roughly 400 million years after the Big Bang, ultraviolet radiation from the first stars and galaxies ionized the surrounding hydrogen gas, transforming the IGM from a neutral to a predominantly ionized state. Observing the present-day IGM allows astronomers to reconstruct the timing, pace, and sources of reionization. Instruments, such as Hubble Space Telescope's Cosmic Origin Spectrograph and the Keck Cosmic Web Imager, have probed high redshift IGM, detecting ionization patterns and metal absorption lines that illuminate the processes of early galaxy formation and feedback. New observational methods are expanding our understanding of the IGM. Fast radio bursts, or FRBs, millisecond duration pulses of radio waves originating billions of light-years away, are dispersed by free electrons in the IGM. By measuring the dispersion measure dm, astronomers can infer the column density of baryons along the line of sight, providing a direct method to trace previously unobserved baryons. Recent studies using FRBs indicate that roughly 30–40% of the universe's baryons reside in the WIM, consistent with predictions from cosmological simulations. The IGM's distribution closely follows the underlying dark matter framework. Simulations from projects like Illustris, Eagle, and TNG-50 demonstrate that baryonic matter traces the gravitational scaffolding established by dark matter halos and filament. The densest IGM regions align with cluster nodes and galaxy groups, while vast voids contain extremely low-density gas. Comparing observations of the IGM with these simulations allows astronomers to connect visible structures to the invisible dark matter web, providing constraints on cosmic evolution and galaxy formation models. On even larger scales, the IGM acts as the connective tissue of the cosmic web, bridging clusters, superclusters, and isolated galaxies. Observations show that baryons in the IGM contribute to the overall mass density of the universe and affect the dynamics of galaxy motions. Flows along filaments transport gas and metals over hundreds of millions of light-years, providing material for star formation in galaxies and clusters. The study of the IGM is rapidly advancing. High-resolution spectrographs, such as ESPRESSO on the Very Large Telescope, X-ray missions like XRISM, and radio arrays, such as CHIME and the Square Kilometre Array, allow astronomers to map intergalactic gas with unprecedented precision. Observations now reveal complex flows along filaments, small-scale turbulence, ionization fronts, and metal enrichment gradients, demonstrating the dynamic and evolving properties of the IGM over cosmological timescales. Dark matter, the invisible hand shaping galaxies. Every galaxy, from sprawling spirals to faint dwarf systems, owes much of its existence to an unseen yet dominant force, dark matter. Though invisible to telescopes, dark matter constitutes roughly 27% of the universe's total mass-energy content, vastly outweighing all ordinary matter, which makes up only about 5%. Its gravitational influence governs the formation, structure, and motion of galaxies, clusters, and even the cosmic web itself. Observations of galactic rotation curves, galaxy clustering, and large-scale structure all provide evidence of dark matter's influence across billions of light-years. The first hints of dark matter appeared in the early 20th century. Observations of galaxy clusters by Fritz Zwicky in the 1930 seconds revealed that galaxies in the Coma cluster moved far too rapidly to be bound by the mass of visible stars and gas alone. Zwicky concluded that a substantial amount of unseen mass, Dunkel Materiae, must exist to prevent the cluster from flying apart. Later, in the 1970 seconds and 1980 seconds, Vera Rubin and collaborators measured the rotation curves of spiral galaxies, showing that stars at the outskirts orbit at nearly constant speeds rather than slowing down as expected. In the Milky Way, stars at a distance of 20 kiloparsecs from the galactic center travel at roughly 220 kilometers per second, far faster than can be explained by the visible disk, indicating a massive halo of invisible matter. Unlike ordinary matter, dark matter does not interact via electromagnetism. It does not emit, absorb, or reflect light. Its interactions are primarily gravitational, making it extremely difficult to detect directly. Decades of experiments, including Xenont, Lux Zeppelin, and Axion searches like ADMX, have yet to identify the specific particle. Leading candidates include weakly interacting massive particles, with masses in the range of 10 GeV to 1 TeV, as well as ultralight axions, with masses below 10, -4 electron volts. Some theories also suggest sterile neutrinos, or primordial black holes, as contributors to the dark matter budget, though these remain speculative. The structure and evolution of galaxies are dictated by dark matter halos. These halos serve as gravitational scaffolds, allowing baryonic gas to cool and collapse into stars, clusters, and ultimately entire galaxies. Simulations such as Illustris, Eagle, and TNG-50 show that without dark matter, gas disperses and star formation is inefficient, leaving no coherent galactic structures. Dark matter halos vary in mass from 8 solar masses for dwarf galaxies to over 15 solar masses for massive galaxy clusters, demonstrating that dark matter operates across an extraordinary range of scales. In galaxy clusters, dark matter dominates the total mass. The Bullet cluster 1E0657-56 provides one of the clearest confirmations. During a collision between two clusters, X-ray observations from Chandra reveal the hot intracluster gas trailing behind the colliding cores, while gravitational lensing maps show that most mass resides in regions coinciding with the dark matter halos, not the luminous gas. In clusters like Coma, Abell 1689, and Perseus, dark matter accounts for roughly 80–85% of the total mass, profoundly influencing galaxy motions, cluster dynamics, and the distribution of hot gas. Dark matter also organizes the cosmic web, the vast network of filaments connecting galaxies and clusters across hundreds of millions of light-years. Baryonic gas flows along these filaments, sustaining star formation in galaxies embedded within them. Observations from the Sloan Digital Sky Survey and Dark Energy Survey reveal that galaxies trace these filaments closely, with denser regions containing more massive halos. High-resolution simulations indicate that the largest filaments can extend up to 400 million light-years, providing the highways along which gas, dark matter, and even smaller galaxies migrate. Dwarf galaxies offer particularly revealing laboratories for dark matter research. Ultra-faint dwarfs, like Segway 1, Reticulum 2, and Draco, may contain only a few thousand stars, yet reside in halos exceeding 10·8 solar masses, implying mass-to-light ratios of hundreds or even thousands. Their velocity dispersions and survival in the Milky Way's tidal field demonstrate dark matter's gravitational dominance, providing constraints on particle properties and ruling out models of warm or hot dark matter in certain cases. Observing these dwarfs with instruments like Keck Observatory, Hubble, and Gaia allows astronomers to study dark matter in environments where ordinary matter is minimal. Dark matter also shapes galactic mergers. When galaxies collide, their stars and gas interact through friction and dissipation, forming tidal tails, starburst regions, and sometimes central black holes. Dark matter halos, however, pass through largely unimpeded, maintaining the overall gravitational potential. Simulations show that in massive mergers, dark matter halos can extend over 1–2 megaparsecs, and the halo's mass distribution can be traced independently from the interacting baryonic matter. Beyond individual galaxies, dark matter governs galactic rotation and morphology. Spiral galaxies retain flat, stable disks because dark matter provides the necessary gravitational support. Without it, stars at the edges would escape and spiral arms would dissipate. Elliptical galaxies rely on their halos to maintain cohesion against internal pressure and tidal forces, while clusters depend on dark matter to prevent member galaxies from drifting apart. Observations indicate that typical dark matter halo densities decrease with radius, following the Navarro-Frank-White NFW profile, yet dominate the outskirts of galaxies where visible matter is sparse. Gravitational lensing surveys, including the Hubble Frontier Fields, CFHT Lens, and KIDS, map dark matter across cosmic scales. Measurements of the cosmic microwave background from Planck indicate a dark matter density parameter omega dm is approximately equal to 0.27, consistent with observations of galaxy clustering, baryon acoustic oscillations, and intergalactic medium studies. Lyman alpha forest surveys trace gas flowing along dark matter filaments, revealing the underlying scaffolding that governs galaxy formation. Indirect detection efforts continue to expand, with Fermilat, AMS-02, and Veritas searching for gamma rays and cosmic rays, potentially produced by dark matter annihilation. While no definitive signals have been found, these experiments constrain cross-sections, particle masses, and decay rates, refining our understanding of dark matter's properties. Observations of galactic rotation curves, cluster dynamics, cosmic web filaments, and the hierarchical assembly of galaxies all demonstrate dark matter's influence. Dark matter halos have been measured in systems ranging from ultra-faint dwarf galaxies, 10·8 solar masses, to superclusters is greater than 10·15 solar masses, providing a quantitative view of its role across cosmic scales. Dark energy, the force driving universal expansion. Beyond the influence of visible matter and dark matter lies another component of the cosmos: dark energy. Dark energy is the dominant force shaping the large-scale structure of the universe. Unlike gravity, which pulls matter together, dark energy drives the accelerated expansion of space itself, influencing the motion of galaxies and the evolution of cosmic structures. Its discovery showed that the universe is expanding at an accelerating rate. The discovery of dark energy arose from observations of type Ia supernovae in the late 1990 seconds. These stellar explosions, resulting from the thermonuclear detonation of white dwarfs in binary systems, act as standard candles due to their consistent peak luminosity. Surveys led by teams such as the Supernova Cosmology Project and the High-Z Supernova Search Team measured the apparent brightness of distant supernovae at redshifts of Z is approximately equal to 0.5, 1.2, corresponding to light emitted 5.8 billion years ago. The surprising result was that these supernovae were fainter than expected, indicating that the universe's expansion had accelerated over time rather than decelerated under gravity. This observation provided the first concrete evidence for dark energy, earning Saul Perlmutter, Brian Schmidt, and Adam Riess the 2011 Nobel Prize in Physics. One leading explanation is the cosmological constant, a concept introduced by Albert Einstein in 1917 as a modification to his equations of general relativity. The cosmological constant represents a uniform energy density filling space, exerting a constant repulsive pressure. Alternatively, some theorists propose quintessence, a dynamic, time-evolving scalar field that could vary in strength across space and time. Other possibilities include modifications of general relativity on cosmic scales, such as FR gravity, or extra-dimensional models. Observations across cosmic history are used to constrain these properties. Dark energy operates on the largest scales, where the universe is relatively homogeneous. Within clusters and superclusters, gravitational attraction dominates locally, binding galaxies together. However, on scales above roughly 100–200 megaparsecs, dark energy overcomes gravity, stretching space and increasing the separation between unbound structures. Measurements of the Hubble constant h0, the current expansion rate of the universe, are directly related to dark energy's effects. Observations from the Hubble Space Telescope and Cepheid variable stars indicate h0 is approximately equal to 73 kilometers s/MPC, while measurements from the Planck satellite of the cosmic microwave background suggest h0 is approximately equal to 67.4 kilometers MPC, creating the so-called Hubble tension. This discrepancy may hint at unknown physics in the early universe, or a dynamic property of dark energy itself. Large-scale cosmological simulations, including Millennium, Illustris TNG, and Horizon AGN, incorporate both dark matter and dark energy to reproduce the observed filamentary structure of the cosmic web. These models show that dark energy reduces the clumpiness of the universe and affects predictions for galaxy clustering and cluster formation. Galaxies currently receding at velocities exceeding the speed of light due to cosmic expansion will eventually become unreachable, slipping beyond the cosmic event horizon. Calculations indicate that galaxies currently at redshift Z is approximately equal to 1.52 are approaching this boundary, leaving only gravitationally bound structures such as the Milky Way, Andromeda, and nearby dwarf galaxies accessible to observation. Observational evidence for dark energy comes from multiple independent methods. Type Ia supernovae surveys, such as the Pantheon Plus compilation, trace the expansion rate over cosmic history. Baryon acoustic oscillations, or BAO, imprinted as a 150 megaparsec scale feature in the galaxy distribution, act as a cosmic ruler to measure distance and expansion. Weak gravitational lensing surveys, including DES, KIDS, and HSC probe the growth of structure and its suppression by dark energy. In combination with CMB measurements from Planck and cross-correlations with galaxy clusters, these approaches map how dark energy has influenced cosmic expansion and structure formation over billions of years. The interplay between dark energy and dark matter is critical to the universe's evolution. Dark matter forms the scaffolding for galaxies and clusters, while dark energy governs the expansion of space, determining how these structures drift apart over time. This balance between attraction and repulsion shapes not only the arrangement of galaxies in the cosmic web, but also the evolution of voids regions, nearly devoid of galaxies. Observations suggest that voids occupy roughly 60% of cosmic volume, expanding faster than average under the influence of dark energy and offering natural laboratories to test its effects. Galaxy clusters themselves provide insights into dark energy. Massive clusters like Abell 1689, Coma, and Max J 717, 5 plus 3745, remain gravitationally bound despite cosmic expansion, but unbound galaxies in voids drift increasingly apart. By tracking cluster mass, growth rates, and number density across redshifts, Z is approximately equal to 0.11. Astronomers constrain the strength of dark energy and its potential evolution over time. Current observations suggest that dark energy behaves very similarly to a cosmological constant W is approximately equal to -1. But slight deviations remain possible and are under intense investigation. The Euclid spacecraft, launched by the European Space Agency, aims to map billions of galaxies across 15,000 square degrees, measuring redshifts, galaxy shapes, and clustering to quantify cosmic acceleration. Similarly, NASA's Nancy Grace Roman Space Telescope, set to survey 2,000 square degrees with high-resolution imaging and spectroscopy, will combine supernovae, BAO, and weak lensing measurements to constrain dark energy parameters. These missions are designed to improve measurements of cosmic acceleration and dark energy properties, the edge of the observable universe, reaching the cosmic horizon. The universe is vast beyond comprehension, stretching across billions of light years in every direction. Yet, as expansive as it is, our view of the cosmos is limited to a boundary known as the observable universe. This cosmic horizon defines the farthest regions that can be detected from Earth, shaped by the finite speed of light, the finite age of the universe, and the ongoing expansion of space. Studying this boundary provides a window not only into the most distant galaxies, but also into the earliest moments of cosmic history, offering clues about the formation of stars, galaxies, and the large-scale structure of the universe itself. The concept of the observable universe originates from a simple principle. Light takes time to travel. When astronomers observe galaxies billions of light years away, they are seeing them as they were in the past, sometimes just a few 100 million years after the Big Bang. Observing distant galaxies allows astronomers to study the evolution of cosmic structures over 13.8 billion years. The farther away an object lies, the further back in time we observe it, providing information about the conditions of the early universe. Current measurements place the radius of the observable universe at approximately 46.5 billion light-years. This apparent discrepancy arises from cosmic expansion. Space itself stretches, carrying galaxies farther from us while light traverses the intervening distance. Within this spherical volume reside roughly 400 billion galaxies, each containing millions to hundreds of billions of stars, along with gas, dust, and dark matter halos. While the observable horizon defines what we can see, it is not a physical boundary. The universe may continue infinitely beyond what is detectable. Exploring the cosmic horizon requires advanced observational tools. Space telescopes such as the Hubble Space Telescope, the Spitzer Space Telescope, and the James Webb Space Telescope capture faint light from the universe's earliest galaxies. Ground-based observatories like the Keck Observatory, Very Large Telescope, and Subaru Telescope complement these observations, particularly in infrared and spectroscopic studies. Light from the most distant galaxies is strongly redshifted, stretched to longer wavelengths due to the expansion of space. Measuring these redshifts provides both distance estimates and insight into the rate of cosmic expansion over billions of years. At the edge of visibility, galaxies appear small, faint, and extremely ancient. Many of these systems formed within 400–600 million years after the Big Bang, during a period known as the Cosmic Dawn, when the first generations of stars and galaxies began to shine. These early objects contributed to the process of reionization, during which ultraviolet light from stars ionized neutral hydrogen in the intergalactic medium, making the universe transparent to radiation. Observing such galaxies allows astronomers to reconstruct the timeline of star formation, heavy element production, and the initial assembly of cosmic structures. The cosmic microwave background defines another type of boundary in the observable universe. Detected by Arno Penzias and Robert Wilson in 1965, and measured in detail by missions such as COBE, WMAP, and Planck, the CMB represents the leftover heat from the Big Bang, emitted roughly 380,000 years after the universe's birth. Tiny fluctuations in this radiation reflect primordial density variations, which seeded the formation of galaxies and large-scale structures. By analyzing the CMB's temperature and polarization patterns, astronomers gain insight into the universe's composition, geometry, and early expansion rate, offering a complementary view of the universe's farthest reaches. The expansion of space, driven by dark energy, further influences the observable horizon. As the universe accelerates, regions at the edge of visibility recede faster than the speed of light relative to Earth, rendering them permanently unreachable. Some galaxies that are currently observable will eventually disappear from view. The changing visibility of galaxies results from the interplay between gravitational attraction and dark energy. Measuring distances at such extreme scales requires a combination of techniques. Type Ia supernovae remain crucial as standard candles, while baryon acoustic oscillations, imprinted as a characteristic scale of roughly 150 megaparsecs in galaxy clustering, act as a cosmic ruler. Redshift surveys, such as the Sloan Digital Sky Survey and Dark Energy Survey, chart the three-dimensional distribution of galaxies across billions of light-years, producing maps of the cosmic web that reveal filaments, voids, and clusters. These methods provide measurements of galaxy positions and large-scale structure over cosmic time. The most distant galaxies, with redshifts exceeding Z, is approximately equal to 10, provide direct insight into the first billion years of cosmic history. Some early galaxies are surprisingly massive, containing billions of stars, while others are tiny, primitive systems dominated by young, hot stars. Observations of these galaxies reveal the early growth of supermassive black holes, some reaching 10–9 solar masses within 800 million years after the Big Bang. Such discoveries challenge theoretical models of galaxy formation and suggest that early structures grew more rapidly than previously thought. Gravitational lensing becomes particularly powerful near the cosmic horizon. Massive clusters like Abell 2744 and MaxJ 1149, 5 plus 2223 bend light from even more distant galaxies, magnifying them by factors of 10–100. This natural cosmic telescope allows astronomers to detect galaxies that would otherwise be invisible and provides indirect measurements of dark matter distribution and mass in the early universe. Lensing studies, combined with JWST observations, can detect galaxies forming within 200–300 million years after the Big Bang. Technological advances continue to push the observable horizon further. JWST, with its infrared sensitivity, has already detected galaxies at redshifts Z is greater than 13, corresponding to light emitted only 300–400 million years after the Big Bang. Future facilities, such as the Extremely Large Telescope or ELT, the 30-meter telescope or TMT, and space missions like LUVOIR, aim to observe even fainter galaxies, map the distribution of dark matter at high redshift, and reveal the processes that shaped the earliest stars and galaxies. These instruments are expected to provide observations of previously undetected early galaxies and their environments. The edge of the observable universe defines the maximum distance from which light has reached Earth. Photons from these regions provide information about early stars, galaxies, and the evolution of cosmic structures over billions of years. Observations of this horizon allow astronomers to study the universe's expansion, structure formation, and the development of stars, galaxies, and planetary systems. Hidden galaxies, discovering the universe beyond visible light. For centuries, astronomers relied primarily on visible light to study the universe, observing stars, nebulae, and galaxies through optical telescopes. Yet, much of the cosmos remains invisible to human eyes. Dust-obscured regions, extremely distant galaxies, and objects emitting predominantly in non-optical wavelengths constitute a vast hidden universe. Exploring beyond visible light has revolutionized our understanding of galaxies, revealing a complexity and diversity that optical observations alone could never capture. Infrared astronomy was among the first windows into this hidden cosmos. Infrared light penetrates dense dust clouds that obscure stellar nurseries and galactic centers at optical wavelengths. Space-based observatories, beginning with the Infrared Astronomical Satellite or IRAS in 1983, and continuing with the Spitzer Space Telescope, Herschel, and now the James Webb Space Telescope, have revealed galaxies shrouded in dust, forming stars at extraordinary rates. Many of these are ultra-luminous infrared galaxies, producing hundreds or even thousands of solar masses of stars per year, compared to the Milky Way's modest rate of roughly 1–2 solar masses per year. Some ULERGs, like ARP 220, form stars so rapidly that they could assemble the mass of the Milky Way in just a few hundred million years. Beyond infrared, radio astronomy uncovers another hidden layer of the universe. Neutral hydrogen gas, the raw material for star formation, emits radiation at a wavelength of 21 centimeters. Radio telescopes such as the Very Large Array or VLA in New Mexico, the Giant Metrowave Radio Telescope or GMRT in India, and the upcoming Square Kilometre Array or SKA allow astronomers to map the distribution of hydrogen across billions of light years. This technique reveals galaxy structure, rotation, and the dynamics of otherwise invisible systems. Radio observations also detect active galactic nuclei powered by supermassive black holes, which can emit jets spanning hundreds of thousands of light years. Some of these jets produce radio emissions millions of times brighter than the galaxy itself, completely hidden in optical light. A notable example is M87, whose central black hole launches a relativistic jet observed across radio, optical, and X-ray bands. High-energy observations, such as X-ray and gamma-ray astronomy, uncover extreme environments otherwise invisible in optical light. X-ray observatories, including Chandra, XMM Newton, and Nuster, detect hot gas in galactic cores and the accretion disks of supermassive black holes, revealing how these energetic objects shape galaxy evolution. Gamma-ray telescopes, like Fermi, probe phenomena such as gamma-ray bursts, supernova explosions, and relativistic jets from distant galaxies. Many of these energetic galaxies are located billions of light-years away, their optical light too faint or obscured to detect, yet their high-energy emissions provide crucial insights into the processes driving galaxy formation and evolution. Another population of hidden galaxies consists of low-surface brightness galaxies, or LSBGs. These systems have stars dispersed across large volumes, making them faint and difficult to detect in visible light. Surveys in multiple wavelengths, including radio and infrared, suggest that LSBGs may be more numerous than previously thought, potentially outnumbering bright galaxies in the local universe. Their discovery challenges models of galaxy formation and emphasizes the importance of multi-wavelength observations to construct a complete cosmic census. Infrared and radio data reveal star formation rates, gas content, and galactic rotation, while X-ray and gamma-ray observations highlight energetic phenomena such as black hole growth and galactic mergers. Combined with optical observations, astronomers can study the life cycle of galaxies, from the accumulation of gas to the formation of stars, planets, and central supermassive black holes. Millimeter and submillimeter observations have further expanded our view of obscured galaxies. Instruments like the Atacama Large Millimeter Submillimeter Array detect cold gas and dust, the raw material for future star formation, in galaxies both near and far. ALMA has observed massive reservoirs of molecular gas in galaxies at redshifts. Z is approximately equal to 6-7, less than a billion years after the Big Bang, indicating that star formation in the early universe was already proceeding at remarkable rates. These observations allow astronomers to study galaxies in formative stages, revealing the processes that will shape their evolution over billions of years. Dense cosmic environments, such as galaxy clusters and superclusters, often harbor hidden systems obscured by intergalactic gas and dust. Multi-wavelength surveys of regions like the Coma Cluster or Abell 1689 reveal mergers, starbursts, and AGN activity that optical observations alone miss. Understanding these environments is critical for tracing how galaxy evolution is influenced by surroundings, from interactions with neighboring galaxies to the effects of cluster-scale gas dynamics. Hidden galaxies are not limited to nearby or dust-shrouded systems. Extremely distant galaxies, whose light has been redshifted into infrared or radio bands by cosmic expansion, provide a glimpse of the universe's first few 100 million years. JWST has already identified galaxies at redshifts exceeding Z equals 13, corresponding to just 400 million years after the Big Bang. Observations of these primordial systems illuminate the earliest stages of star formation, the assembly of galactic structures, and the process of cosmic reionization. Many of these galaxies were undetectable by the Hubble Space Telescope, demonstrating the capabilities of modern infrared and radio observatories. Accounting for hidden galaxies improves estimates of the scale of the universe. Optical surveys alone miss a significant fraction of star-forming activity, obscured systems, and faint galaxies, potentially underestimating cosmic star formation rates by factors of 2 or more. By combining optical, infrared, radio, X-ray, and gamma-ray observations, astronomers achieve a multidimensional view of the cosmos, revealing the full spectrum of galactic activity and the underlying processes shaping cosmic history. Hidden galaxies also offer insights into the evolution of large-scale structure. By tracing the distribution of dust-obscured star-forming galaxies and AGN across cosmic filaments and voids, researchers gain a better understanding of how the cosmic web evolves over time. Surveys like Cosmos, GOODS, and Alpine integrate multi-wavelength data, revealing interactions, mergers, and the growth of stellar mass across billions of years, connecting hidden processes to observable structures. Galaxies through time. unraveling billions of years of evolution. Galaxies are far from static. They are dynamic systems evolving over billions of years. By observing galaxies at different distances, astronomers effectively peer into the past, with each photon serving as a snapshot of an earlier cosmic era. This look-back time allows scientists to reconstruct the universe's history, revealing the formation, growth, and transformation of galaxies across billions of years. A central tool in studying galactic evolution is the measurement of redshift Z. As the universe expands, the wavelength of light from distant galaxies stretches, shifting toward the red end of the spectrum. The degree of redshift directly corresponds to both distance and look-back time. A galaxy at Z is approximately equal to 0.1 is seen as it was roughly 1.3 billion years ago, while one at Z is approximately equal to 10 existed less than 500 million years after the Big Bang. Observations across a wide redshift range quantify properties such as star formation rate, gas content, and stellar mass at different epochs. The earliest observable galaxies are often protogalaxies, small, irregular, and gas-rich systems with high star formation rates. Observations with the James Webb Space Telescope and the Atacama Large Millimeter, Submillimeter Array reveal that galaxies at Z is greater than 7 frequently display clumpy morphologies, with star formation concentrated in dense regions. These early systems can produce hundreds of solar masses of stars per year, far surpassing the Milky Way's current rate of roughly 1-2 solar masses per year. Measurements indicate high densities of star-forming gas and rapid stellar production in these galaxies. As galaxies mature, they often develop more organized structures. Spiral galaxies, like the Milky Way and NGC 6744, exhibit well-defined disks and arms, while elliptical galaxies such as M87 emerge primarily from mergers and interactions that disrupt stellar orbits and erase spiral structure. Observing galaxy populations at different redshifts reveals trends in morphology, star formation, and mass distribution. Surveys from the Hubble Deep Field, Cosmos, and CANDELS document that early galaxies were smaller, more irregular, and more gas-rich, while later galaxies display more extended disks and spheroidal structures. Galaxy mergers play a pivotal role in this evolution. Collisions can trigger intense bursts of star formation, fuel the growth of central supermassive black holes, and alter galactic structure. Observations indicate that mergers were far more frequent in the early universe. At Z is approximately equal to 2, 3, nearly 20–30% of massive galaxies were undergoing major mergers. Interacting systems such as the antennae galaxies NGC 4038/4039 exemplify how mergers can funnel gas into central regions, ignite starbursts, and eventually produce more massive spheroidal galaxies. These interactions are central to hierarchical models of galaxy formation, where large galaxies grow from the successive merging of smaller progenitors. Chemical evolution is another key component of galactic history. The first generations of stars synthesized light elements into heavier ones, enriching the interstellar medium. Subsequent stars incorporated these metals, enabling the formation of planets and complex systems. Spectroscopic studies of distant galaxies using instruments like Keck Observatory's Deimos spectrograph and VLT, MUSE reveal that metallicity steadily increased over cosmic time. Galaxies at Z is approximately equal to 6-7, typically contain only 10–20% of the Milky Way's current heavy element abundance, while systems at Z is approximately equal to 1–2 show near-solar metallicities, reflecting the cumulative enrichment from billions of years of star formation. Dark matter provides the gravitational scaffolding for galactic evolution. Galaxies form within dark matter halos, whose mass and distribution guide the accumulation of gas and stars. Observations of rotation curves and large-scale clustering indicate that dark matter influences both the growth of individual galaxies and the assembly of galaxy clusters. For example, studies of dwarf galaxies in the local group reveal high dark matter fractions up to 99% of total mass, in some cases emphasizing its role in shaping galactic structure even in the smallest systems. The star formation history of the universe offers further insights. Observations show a peak in star formation roughly 2-3 billion years after the Big Bang, a period referred to as cosmic noon, when galaxies were most actively forming stars. Star formation rates during this epoch reach tens to hundreds of solar masses per year in typical galaxies, compared to only a few solar masses per year in the present-day universe. After this peak, the cosmic star formation rate declined steadily due to gas depletion, feedback from supernovae, and the energetic effects of active galactic nuclei. Surveys such as SDSS, Galaxies, and ALMA provide quantitative measurements of these trends, enabling detailed models of stellar production and galactic evolution. Galaxies also evolve in response to their environments. Dense clusters, like the Coma cluster or Virgo cluster, often quench star formation earlier due to ram pressure stripping and tidal interactions, producing populations of red, passive galaxies. In contrast, isolated or field galaxies can sustain star formation for longer periods, highlighting the complex interplay between internal processes like gas cooling and supernova feedback and external influences from surrounding structures. Environmental effects also shape morphology. Spirals dominate low-density regions, while ellipticals prevail in dense clusters. Advances in integral field spectroscopy, or IFS, have improved the study of galactic kinematics across cosmic time. Instruments such as MUSE on the Very Large Telescope and KCWI on Keck allow astronomers to map stellar motions, gas flows, and velocity dispersions in distant galaxies. These data show the properties of disks, the stabilization of rotational structures, and the diversity of kinematic states in early galaxies. For example, studies of galaxies at Z is approximately equal to 1,3 indicate that disk formation was underway in some systems, while others remain turbulent and irregular. Scaling relations further provide measurable parameters for galaxy growth. The Tully-Fisher relation connects rotational velocity to luminosity in spirals, while the mass-metallicity relation links stellar mass to chemical composition. Observations show that these relationships persist across cosmic time, including at high redshift, offering constraints for theoretical models of galaxy formation. Galactic evolution, predicting the future of the cosmos. Galaxies, though colossal and seemingly eternal, are subject to processes that govern their long-term destiny. While contemporary astronomy provides a detailed record of their past evolution, it also offers a predictive window into the future. By combining observations, computational simulations, and fundamental physics, astronomers can anticipate how galaxies will evolve, interact, and ultimately fade over the next tens of billions to trillions of years. One of the primary forces shaping the future of galaxies is mergers. Gravity inexorably pulls galaxies toward one another, reshaping structures and igniting transformative events. The Milky Way itself is on a collision course with the Andromeda Galaxy, currently approaching at approximately 110 kilometers per second. Simulations from the NASA ESA Hubble Space Telescope suggest the merger will occur in about 4-5 billion years, resulting in a massive elliptical galaxy sometimes nicknamed Milkomeda. During such interactions, tidal forces will distort stellar orbits, gas clouds will compress to trigger bursts of star formation, potentially hundreds of solar masses per year, and central black holes may merge, releasing gravitational waves detectable across intergalactic distances. This scenario exemplifies the hierarchical growth that has been a consistent feature of the universe. Small galaxies coalesce into larger ones, forming the colossal systems we observe in galaxy clusters today. Another determinant of galactic fate is the decline of star formation. Star formation relies on cold molecular gas, primarily hydrogen, which is gradually consumed by successive generations of stars. In many galaxies, particularly massive ellipticals, such as M87 in the Virgo cluster, star formation has effectively ceased, leaving stellar populations dominated by old red stars. Observations indicate that the most massive galaxies formed the bulk of their stars within the first 2-3 billion years after the Big Bang, and have since experienced minimal new star formation. The combination of supernova feedback, which expels gas, and active galactic nuclei activity, which heats or removes gas, contributes to the transformation of galaxies into these quiescent, red and dead systems. Environmental factors influence galaxy evolution. Galaxies in dense clusters experience more gravitational interactions, ram pressure stripping, and mergers. The Coma cluster, containing over 1,000 galaxies, is dominated by massive ellipticals, many of which have lost their gas due to repeated encounters and the cluster's intra-cluster medium. In contrast, isolated galaxies such as NGC 2000, 403 inches, the M81 group retain gas longer, allowing star formation to continue for several billion years. The growth of supermassive black holes is another critical influence. Central black holes, ranging from millions to billions of solar masses, regulate galactic evolution through feedback. When accreting matter, black holes produce energetic jets and radiation that can expel gas from the galaxy or prevent cooling, effectively halting star formation. The quasar phase, common in the early universe, exemplifies this effect. Intense energy output regulates galactic growth, setting the stage for eventual quiescence. Future mergers will often result in the coalescence of these central black holes, releasing gravitational waves and further influencing galactic structure. On a cosmological scale, the expansion of the universe, driven by dark energy, affects the visibility of galaxies. Current measurements indicate a Hubble constant of roughly 70 kilometers s/MPC, and observations from Planck and Type Ia supernovae suggest that the universe's expansion is accelerating. Over the next tens of billions of years, galaxies beyond the local group will recede faster than light relative to us, moving beyond the cosmic horizon. Smaller galaxies experience absorption into larger systems or disruption by tidal forces. Dwarf galaxies, such as the Sagittarius dwarf currently merging with the Milky Way, contribute stars, gas, and dark matter to their host, altering chemical composition, stellar populations, and dynamical properties. Stellar evolution also dictates the long-term fate of galaxies. Stars exhaust their nuclear fuel, leaving remnants such as white dwarfs, neutron stars, or black holes. Massive stars die quickly in supernova explosions, seeding the interstellar medium with heavy elements, while low-mass stars, such as red dwarfs, can persist for trillions of years. Over cosmological timescales, star formation will eventually cease entirely in many galaxies, leaving a dim population of aging stars. Models predict that in 100 trillion years, the universe will be populated predominantly by stellar remnants, with only faint cooling white dwarfs and neutron stars emitting light. Interactions with intergalactic gas continue to influence galaxies' trajectories. Gas inflows from filaments of the cosmic web can temporarily rejuvenate star formation or fuel AGNs, while supernovae-driven winds and black hole outflows remove material. These processes modulate growth and activity over billions of years. Simulations using the illustrious TNG and Eagle frameworks show that galaxies experiencing frequent gas replenishment can sustain star formation longer, while isolated systems eventually run out of fuel and transition to quiescence. Looking further into the distant future, Simulations predict that hierarchical mergers will yield enormous elliptical galaxies at the centers of clusters, surrounded by smaller satellite galaxies. For instance, a galaxy cluster like Virgo may eventually coalesce into a single supergiant elliptical over the next tens of trillions of years, with star formation nearly extinct and luminosity declining steadily. Isolated galaxies will linger longer, but without fresh gas, even they will become increasingly faint, dominated by long-lived red dwarfs and compact remnants. Astrophysical modeling, incorporating gravity, thermodynamics, stellar evolution, black hole physics, and dark energy, enables predictions of long-term galactic evolution. Simulations and observational constraints indicate outcomes such as the eventual merger of the Milky Way and Andromeda, the dimming of galactic light, and changes in the observable universe due to accelerated expansion. The study of galactic fate extends beyond academic curiosity. It informs our understanding of cosmic structure, matter cycles, and the interplay of fundamental forces over the longest timescales. It illustrates how processes observed locally today, from star formation to black hole activity, will govern the universe's evolution billions and trillions of years into the future. Beyond the horizon, exploring the universe's farthest galaxies, the universe that humanity observes today is immense, yet our understanding of it has only scratched the surface. Over the past century, advances in telescopes, detectors, and data analysis have expanded our cosmic map from a few nearby galaxies to billions across the observable universe. Yet even this vast dataset represents only a fraction of what exists. The ultimate frontier lies beyond the cosmic horizon, the boundary beyond which light has not yet had time to reach us since the Big Bang. Galaxies beyond this limit remain invisible, yet their presence can be inferred through the mathematics of cosmology, simulations of cosmic evolution, and the behavior of large-scale structures. The cosmic horizon is a fundamental concept in modern astronomy. Light travels at a finite speed. Because space itself stretches, many regions are now so distant that photons emitted there will never reach Earth. Current models suggest the observable universe spans a radius of roughly 46.5 billion light-years, but beyond this lies an even vast volume of galaxies yet unseen. Advanced observational techniques aim to probe ever closer to this limit, revealing galaxies that existed when the universe was less than 1 billion years old. Technological innovation is central to this endeavor. The James Webb Space Telescope has already begun to transform our understanding, detecting galaxies at redshifts above 13, corresponding to just 300–400 million years after the Big Bang. Complementing JWST, the Vera C. Rubin Observatory will survey the sky repeatedly, producing a dynamic map of transient events and faint galaxies across 18,000 square degrees of the sky. The Square Kilometre Array, with its unprecedented sensitivity to radio waves, is expected to detect neutral hydrogen in the earliest galaxies, tracing their gas reservoirs and star formation over cosmic time. By combining data from multiple wavelengths, infrared, optical, ultraviolet, X-ray, and radio astronomers can reconstruct the formation history of galaxies, revealing the hidden structure of the universe. Beyond instrumentation, computational tools have become essential. Surveys like LSST, or Legacy Survey of Space and Time, and the data from JWST generate petabytes of information, requiring artificial intelligence and machine learning to manage. Algorithms can classify galaxy morphology, measure redshifts, identify gravitationally lensed systems, and even detect anomalous structures that might indicate exotic phenomena or previously unknown galaxy types. In 2023, for example, AI-assisted analysis identified over 1,000 previously unobserved galaxies in JWST deep field images. Gravitational lensing offers another natural method to study galaxies beyond the horizon. Massive galaxy clusters act as lenses, bending and magnifying light from galaxies located much farther away. The Hubble Frontier Fields project has exploited this effect to observe galaxies that would otherwise be too faint to detect, revealing star formation rates as high as 100 solar masses per year in some early galaxies. Lensing allows astronomers to study structure formation, supermassive black hole growth, and interstellar medium conditions in galaxies from the universe's first billion years. Humanity's reach may extend further still with next-generation space observatories. Proposed instruments like LUVOIR or Large UV, Optical, IR Surveyor, HABEX or Habitable Exoplanet Observatory, and space-based interferometers aim to detect faint light from the earliest galaxies. Ultra-sensitive X-ray and infrared detectors will probe the growth of the first black holes, the metallicity of primordial stars, and the formation of galaxy clusters in the first few 100 million years. These missions could map galaxies residing at redshifts of 1520, effectively pushing observational limits to within a few 100 million years of the Big Bang. Simulations remain indispensable in guiding these explorations. Large-scale cosmological simulations like Illustris TNG, Eagle, and Blue Tides model the evolution of billions of galaxies, dark matter filaments, and intergalactic gas. They predict the locations and properties of galaxies beyond the observable horizon and provide testable hypotheses for future observations. By comparing models with deep field data, astronomers refine their understanding of star formation, AGN feedback, and the role of dark matter in shaping cosmic structures. Observing galaxies at extreme distances also deepens our understanding of fundamental forces. The distribution, motion, and growth of these galaxies constrain models of dark matter and dark energy, revealing how these invisible components govern cosmic expansion and structure formation. For instance, studies of high redshift galaxies can measure the rate of cosmic acceleration, helping to refine the Hubble constant beyond local measurements. Exploration beyond the horizon is not purely observational. It also drives technological innovation. Adaptive optics, wide-field spectrographs, and next-generation detectors improve sensitivity and resolution, enabling detection of fainter and more distant galaxies. Innovations in computational astrophysics, data pipelines, and AI enhance pattern recognition and predictive modeling, benefiting other scientific disciplines from planetary studies to fundamental physics. Probes and missions designed to explore intergalactic space may further extend our knowledge. Concepts such as deep-field X-ray satellites, infrared interferometers, and gravitational wave observatories promise insights into black hole mergers, intergalactic gas flows, and cosmic structure formation in regions where light is faintest. Even as direct physical exploration remains impossible on human timescales, these instruments allow indirect mapping of galaxies beyond our horizon. Observing systems forming just 200–400 million years after the Big Bang provides insight into the first generations of stars, the assembly of the first galactic cores, and the reionization of the intergalactic medium. Such galaxies provide data on early galaxy clusters, star formation cycles, and black hole growth over billions of years. Galaxies at the edge of the observable universe provide data on the laws of physics, the origin of cosmic structures, and processes shaping the universe from its infancy to the present day. Future telescopes, AI-driven analysis, and advanced observational methods will enable the detection and study of increasingly distant galaxies, clusters, filaments, and voids. Mapping these structures will expand our understanding of the universe's diversity and complexity,